Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and physics unfolds at a pace that never feels in a hurry. Tonight, we're going to settle into a question that has followed humanity from the first flicker of firelight to the glow of modern screens, a question about motion, distance, and a strange, invisible boundary that nothing in the universe seems able to cross. Somewhere out there, in the quiet between stars and the steady hum of atoms, there is a number that rules all journeys, a speed that does not care how strong your engines are, how bold your plans might be, or how much energy you are willing to spend. It simply waits, steady and unbending, like a calm signpost at the edge of possibility. Before we drift to that idea together, take a small moment to notice where you are. Maybe you're lying in a dim room, listening through headphones, or perhaps the sound is coming softly from a speaker nearby. What part of the world is holding you right now, and what time is it there? It is a gentle thought, knowing that this same stream of words can reach across continents and oceans, meeting different clocks and different nights all at once. If you find this quiet exploration soothing, or if it gives your thoughts a place to slow down for a while, you're always welcome to like the video or subscribe, just to help this little pocket of calm find its way to others who might need it too. Now, let's begin moving slowly and carefully toward a limit that defines how the universe itself seems to breathe. At first glance, speed feels like one of the simplest ideas in all of physics. It is just how fast something moves from one place to another. A car travels down a road, a bird crosses the sky, a breeze carries a leaf along a path you did not expect. You can measure it with a watch and a ruler, seconds ticking by as distance slips away beneath motion. For most of everyday life, this idea works perfectly well. You can double your speed by pressing the accelerator, or slow to a stop by easing off the pedal. The world feels flexible, responsive, and open to being pushed just a little bit harder. But the universe, it turns out, does not share that endless flexibility. There is a point where pushing harder stops helping. There is a ceiling, a quiet line in the equations of nature that says, this far and no farther. That line is drawn at the speed of light, about 300,000 kilometers per second, a number so large that it feels almost abstract, and yet so close that it shapes the way every particle, every signal, and every moment of cause and effect unfolds around you. Light itself is a curious place to start. When you turn on a lamp, the room does not fill gradually, like water rising in a glass. Instead, it seems to appear all at once, shadows jumping to new positions, surfaces revealing themselves instantly. But there is a tiny delay, so small that your senses cannot catch it. The light from the bulb races outward in all directions, not as a solid thing, but as a ripple in the electromagnetic field, a travelling pattern of energy and information. It does not need air. It does not need a road. It simply moves, always at the same pace, whether it is crossing your living room or the vast emptiness between galaxies. This constancy is one of the strangest and most important discoveries in physics. No matter how fast you're moving, light still moves away from you at the same speed. If you chase a beam of light in a spaceship, pushing your engines harder and harder, you might expect to see that beam slow down from your perspective, like a car you're catching up to on a highway. But that never happens. The light always pulls away at the same familiar rate, as if the universe itself is quietly adjusting everything else to make sure that number never changes. To understand why this matters, it helps to think about how motion usually works. Imagine you are on a train tossing a ball forward. To someone sitting next to you, the ball moves at the speed of your throw. To someone standing on the platform as the train passes by, the ball moves faster, because it carries both the speed of the throw and the speed of the train. Speeds add up. That is how common sense and classical physics tell the story. But light refuses to play along. No matter how fast the train is moving, no matter how fast you throw the light forward, it still travels at the same speed. This simple, stubborn fact forces the universe to make a compromise somewhere else, and that compromise does not come from slowing down light. Instead, it comes from reshaping space and time themselves. This is where the idea of a universal speed limit begins to feel less like a rule imposed from above, and more like a natural consequence of how reality is built. Space and time are not separate, rigid backdrops where events unfold. They are part of the same flexible structure, often called spacetime, and they adjust in response to motion and energy. As something moves faster, closer and closer to the speed of light, time for that moving object begins to slow down relative to someone who is standing still. Clocks tick more slowly. Processes take longer. At the same time, distances in the direction of motion begin to shrink. A spaceship travelling at extreme speeds becomes shorter along its path of travel, at least from the perspective of an outside observer. These effects are not tricks of measurement. They are built into the structure of space-time itself. The result is a kind of cosmic accounting system. The universe balances the equation so that the speed of light remains constant for everyone, even if that means time and space have to bend a little to make it happen. This balancing act is what sets the ultimate limit. As you try to go faster, the cost is not just more fuel or more powerful engines. The cost is that your own time slows down, and the energy required to keep accelerating grows without bound. Here is where the idea of energy steps quietly into the story. In everyday life, adding energy usually means adding speed. Push a swing harder, and it goes higher. Press the gas pedal, and the car moves faster. There is a comfortable, linear feeling to it, as though effort and result are neatly proportional. But in the relativistic world, near the speed of light, this relationship breaks down. Each additional bit of speed requires more energy than the last. Not just a little more, but dramatically more. The closer you get to that cosmic limit, the steeper the cost becomes, until, at the speed of light itself, the energy required would be infinite. No matter how powerful your engines, no matter how large your fuel supply, you can never reach infinity. The universe does not offer that option. This is not a technical limitation. It is not about materials or engineering or clever design. It is a structural feature of reality. The equations that describe energy and motion simply do not allow an object with mass to be accelerated to the speed of light. The math does not blow up because of a mistake. It blows up because it is pointing at a real, physical boundary. Now, this is where Richard Feynman enters the picture, not as someone who discovered this speed limit, but as someone who had a particular gift for making the strange feel approachable. Feynman was a physicist who loved to take complicated ideas and turn them into stories you could almost hold in your hands. He didn't shy away from the math, but he also believed that understanding meant more than just being able to write down equations. It meant being able to picture what was going on, even if the picture was a little rough around the edges. One of the ways Feynman liked to think about particles was as travellers through space-time, following paths from one event to another. Not just one neat single path, but a whole collection of possible paths, each one contributing in its own way to what we observe. This idea shows up most famously in what are now called Feynman diagrams, simple drawings that map out how particles interact, exchange energy, and influence each other through fundamental forces. In these diagrams, time usually runs in one direction, often drawn as an upward or sideways axis, while space stretches across the other direction. A particle's journey becomes a line, tracing a route through space-time from one moment to the next. When particles interact, their lines meet, exchange something, and then move on. It is a quiet, visual way of telling a story about cause and effect at the smallest scales. What is interesting here is not just the diagrams themselves, but what they quietly assume. Every interaction, every exchange of energy or information respects the structure of space-time. Signals do not jump ahead of their causes. Influences do not arrive before they are sent. The speed of light sits in the background like a referee, making sure that the order of events stays consistent for everyone, no matter how they are moving. If something could travel faster than light, this neat structure would begin to unravel. From some perspectives, an effect could appear before its cause. A message could arrive before it was sent. The tidy story told by those lines in a Feynman diagram would start to loop back on itself in ways that do not make physical sense. This is one of the deeper reasons why the speed of light matters so much. It is not just about how fast things can go. It is about how the universe keeps its events in order. The limit is woven into the way cause and effect are preserved across different points of view. To see why this matters, imagine two observers moving relative to each other, each with their own clock and their own sense of what is happening when. Because time itself depends on motion, they may not agree on which events happen at the same moment. But they will always agree on the order of events that can be connected by a signal travelling at or below the speed of light. If one event can influence another, everyone will agree on which one came first. This shared agreement is what keeps physics consistent. It is what allows you to build a theory where predictions do not depend on who is watching or how fast they are moving. The speed of light is the thread that stitches all those perspectives together into a single, coherent fabric. Feynman often emphasized that the laws of physics should look the same from every point of view. Whether you're standing still, riding in a car, or drifting through space in a spacecraft, the basic rules do not change. The speed of light is part of what makes that possible. It is a universal reference, a number that everyone can agree on, even if they disagree about distances and durations. There is a gentle elegance to this idea. Instead of one privileged viewpoint, one special frame of reference where the real time and space live, the universe offers a kind of democratic structure. Everyone gets their own version of time and distance shaped by their motion, but everyone shares the same fundamental limits. At the level of everyday experience, this can feel very far away. You do not notice your clock slowing down when you walk across the room. You do not see rulers shrink when you drive down the highway. These effects are real, but they are so small at ordinary speeds that they fade into the background of daily life. It is only when you push toward that cosmic speed limit that the universe starts to reveal its deeper design. There is something quietly reassuring about that. The same rules that govern the motion of distant galaxies also govern the tiny movements of electrons in a wire and the steady rhythm of your own heartbeat. The limit is always there, always shaping what is possible, even when you're not thinking about it. Feynman once remarked that nature's imagination is far greater than ours. The speed of light is one of those places where that imagination shows itself, not as a dramatic barrier you can crash into, but as a subtle guide that shapes the entire structure of reality from the inside out. As you sit with this idea, you might find it helpful to let go of the image of a wall or a finish line. The speed of light is not something you race toward. It is more like a horizon that stays at a fixed distance no matter how fast you move. You can approach it, feel its influence more strongly, but it always remains just out of reach, quietly defining the shape of the journey itself. Across the quiet stretch that follows the first idea of a universal speed limit, it becomes natural to wonder what speed really means once space and time are no longer treated as separate solid stages, but as parts of the same flexible structure. In everyday life, speed feels almost too simple to question. You move from one place to another, you glance at a clock, and you divide the distance by the time it took. The result is a number that tells you how fast you are going. This approach works so well in daily experience that it can feel strange to suggest there might be more hiding underneath it. Yet when physics begins to look closely at the deepest layers of reality, even this familiar idea starts to shift and stretch. Before the 20th century, most scientists thought of space and time as fixed and independent. Space was the stage where things happened, and time was the steady drumbeat ticking away in the background. Objects moved through space as time passed, but the two did not mix. Speed, in that picture, was simply how quickly an object changed its position as time flowed along. You could imagine drawing a map of the world, placing a dot where something started, another dot where it ended, and then measuring the path between them. The clock told you how long it took, and that was that. This view matched experience so closely that it felt almost unnecessary to question it. If you walk across a room, the floor does not seem to stretch or shrink. If you wait for a kettle to boil, the seconds do not seem to care whether you're standing still or pacing back and forth. Space and time feel solid and reliable, like two separate tools you can use whenever you need them. But the universe, it turns out, does not treat them as separate at all. Instead, it weaves them together into a single fabric, where movement through space and movement through time are deeply connected. This idea can be approached gently, without diving straight into equations or complex geometry, by thinking about what it means to exist at all. Every object, including you, is always moving through space-time. Even when you're sitting perfectly still in a chair, not shifting a muscle, you're still travelling forward in time. That forward motion is constant and unavoidable. You cannot pause it. You cannot turn it around. You move from one moment to the next at a steady pace, carried along by the structure of the universe itself. In this sense, motion is not just something that happens when you change location. It is something that happens simply by existing. Physics often describes this by saying that everything has a kind of total motion through space-time. When you move through space, some of that motion is redirected away from time. When you slow down in space, more of it is directed into the flow of time. This is not just a poetic way of speaking. It is a precise feature of how space-time works. The faster you move through space, the slower you move through time, at least as measured by someone who is not moving alongside you. This trade-off is what lies behind time dilation, the effect where a fast-moving clock ticks more slowly than a stationary one. Now, if speed is the rate at which you move through space, and time is the rate at which you move through time, then in a world where space and time are linked, speed takes on a deeper meaning, becomes part of a larger balance rather than an isolated number. To get a feel for this, imagine space-time as a kind of grid, like a vast sheet marked with lines. One direction on the sheet represents space, another direction represents time. Every object traces out a path on this sheet, called a world line, as it exists from one moment to the next. If you're standing still, your world line goes straight upward through time. You stay in the same place in space, but you move steadily forward in time. If you start walking, your world line tilts. Now, instead of going straight up, it leans over a little, showing that you're moving through both space and time at once. The faster you walk, the more your world line tilts away from the time direction and toward the space direction. There is, however, a limit to how far it can tilt. That limit corresponds to the speed of light. Light's world line sits right on the edge of what is allowed, at a perfect angle that represents moving through space as fast as space-time permits. Nothing with mass can reach that angle. No matter how hard you push, your world line always stays just a little more upright, always retaining some forward motion through time. This picture helps explain why the speed of light is not just a fast number, but a structural feature of reality. It defines the shape of space-time itself. It sets the boundary between what can be connected by cause and effect, and what cannot. Within this framework, speed is not just about how quickly something changes its position. It is about how its path through space-time is oriented. A slow object leans only slightly away from the time direction. A fast object leans more. Light leans as far as possible, right up to the edge of the allowed region. This also sheds light on why adding speeds does not work, the way you might expect when you get close to that limit. In everyday life, you can stack velocities. If you walk forward on a moving train, your speed relative to the ground is the speed of the train plus the speed of your walk. This makes sense in a world where space and time are separate, rigid backdrops. In space-time, however, tilting a world line is not as simple as adding two angles together. The geometry is different. When you try to combine two motions that are already close to the limit, the structure of space-time itself resists. The result is that no matter how you combine them, the final tilt never reaches or exceeds the angle corresponding to the speed of light. This is why, from the perspective of someone chasing a beam of light, that beam still races away at the same speed. The geometry of space-time adjusts the measurements of space and time in just the right way to preserve that limit. It can be helpful to think of this as a kind of built-in coordination system. The universe keeps everything consistent by letting different observers disagree about distances and durations, while making sure they all agree on the fundamental connections between events. Speed, in this deeper sense, becomes a relational quantity. It is not just about how fast something is going in an absolute way. It is about how one observer's measurements of space and time compare to another's. This brings us to the idea of reference frames. A reference frame is essentially a point of view, a way of assigning coordinates to events in space and time. If you're standing on the ground, you have one reference frame. If you're riding in a car, you have another. Each frame comes with its own rulers and clocks, its own way of slicing the world into positions and moments. In classical physics, all reference frames agree on time. They may disagree about positions and speeds, but they share a common ticking clock. In relativistic physics, this shared clock disappears. Each frame carries its own time shaped by its motion. This is not just a philosophical shift, it has practical consequences. Two observers moving relative to each other can disagree about whether two events happened at the same time. What looks simultaneous in one frame may not be simultaneous in another. Despite this, there is still a shared structure. Events that can be connected by a signal travelling at or below the speed of light will maintain the same order in every frame. Everyone will agree on which one came first. This is what preserves causality, the basic rule that causes come before effects. Speed, then, is tied directly to this network of cause and effect. It determines which events can influence which others. It draws invisible cones in space-time, called light cones, that separate the past, the future, and the elsewhere. The past contains all the events that could have influenced you. The future contains all the events you could potentially influence. The elsewhere contains events that are too far away in space-time to have any causal connection with you, at least for now. These cones are defined entirely by the speed of light. They do not care about your personal sense of time or your local measurements of distance. They are part of the deep structure of the universe. From this perspective, speed is not just about motion. It is about connectivity. It is about which parts of the universe can talk to which other parts, and how quickly information can flow between them. This idea becomes even more interesting when you consider what light itself is doing. Light is not just a thing that moves through space. It is the way changes in the electromagnetic field propagate. When an electron in an atom shifts its state, that change ripples outward as light. When a star flares, that disturbance travels across space as a wave of energy and information. In this sense, the speed of light is the speed at which the universe communicates with itself. It is the rate at which one part of reality can become aware of what is happening in another part. Everything else is bound by that rate. No matter how fast a particle moves, no matter how energetic a process becomes, the news of what has happened cannot spread faster than light. This brings us back to energy and its role in motion. In classical physics, energy is often treated as something you can pile on to make things go faster and faster. In relativity, energy does something a little different. As you add energy to a moving object, more and more of that energy goes into changing the way it moves through time, rather than increasing its speed through space. The object's resistance to acceleration increases, its momentum grows faster than its velocity. This is sometimes described by saying that its effective inertia increases, though this is a subtle point and can be misunderstood if taken too literally. What matters is the outcome. The closer you get to the speed of light, the more energy you need for each tiny increase in speed. The curve gets steeper and steeper until it becomes vertical at the limit. This behaviour is not arbitrary. It is a reflection of the geometry of space-time. The equations that describe energy and momentum are built to respect that geometry, to ensure that the speed of light remains an unbreakable boundary. Richard Feynman liked to emphasize that when you see a simple rule like this, a single number that shows up everywhere in physics, it often points to something fundamental. The speed of light appears not just in the study of light, but in the equations for energy, mass, momentum, electricity, magnetism, and even gravity. In Einstein's famous equation, E equals mc squared, the speed of light plays the role of a conversion factor between mass and energy. It tells you how much energy is stored in a given amount of mass. This again ties speed to the deep structure of reality, not just to how fast things move. Mass itself can be thought of as a kind of frozen energy, a store of potential motion through space-time. When you add energy to a system, you are, in a sense, changing the way it occupies space-time. Speed, energy, mass, space, and time are not separate pieces that happen to interact. They are different aspects of a single, unified framework. This unified view also helps explain why the speed of light shows up as a limit even for things that are not made of light. It is not that the universe decided to make photons special. It is that the structure of space-time itself has a built-in scale, a way of relating distances and durations. Light happens to move in a way that reveals that scale directly. When you measure the speed of light, you're really measuring how many units of space correspond to a unit of time in the deepest sense. In modern physics, this is taken so seriously that the meter and the second are defined in terms of the speed of light rather than the other way around. Distance is measured by how long it takes light to travel. This reversal hints at how central this idea has become. Space and time are no longer the foundations on which everything else is built. They are in a way derived from the behaviour of light and the structure of space-time. There is a quiet circularity here. Speed is defined as distance over time. Distance and time are defined using light. Light's behaviour is described by the structure of space-time, and space-time's structure is revealed through the limits on speed. It is a closed loop of ideas, each one supporting the others. From a more grounded point of view, this means that whenever you talk about how fast something is going, you're also, whether you realise it or not, talking about how it fits into the causal structure of the universe. You're talking about which events it can influence and which ones can influence it. A slow-moving object has a narrow reach. It can only affect things nearby in space and time. A fast-moving signal, like light or a radio wave, can reach across continents and planets, stitching together distant regions into a shared present, at least as much as the universe allows. Yet even this reach is limited. The night sky itself is a reminder of that. When you look at a distant star, you're not seeing it as it is now. You're seeing it as it was when the light left it, sometimes years, sometimes thousands or millions of years ago. The speed of light turns the universe into a layered history, where distance is also a measure of time. In this sense, speed becomes a bridge between the present and the past. It determines how far back in time you're looking when you observe something far away. The faster the signal, the thinner that layer becomes, but it can never vanish entirely. This layered view of reality is another way of seeing how deeply speed is woven into the fabric of space and time. It is not just a property of moving objects. It is a property of how the universe reveals itself to itself. It becomes easier to see why the question of faster-than-light motion is not just about building a better engine or finding a clever shortcut. It is about whether the structure of space-time itself can be altered, whether the geometry that ties space, time and causality together can be bent in ways that allow new kinds of connections. Physicists explore these possibilities through ideas like curved space-time, expanding space, and exotic solutions to the equations of gravity. But even there, the speed of light remains a guiding presence, shaping what is allowed and what remains out of reach. For now, it is enough to notice how a simple idea, how fast something moves, opens into a much larger picture. Speed becomes a window into the deep relationship between space and time, a clue that the universe is not built from separate parts, but from a single, interconnected whole. Somewhere along this slow unfolding of how speed, space and time lean into one another, it becomes almost impossible not to turn your attention back to the quiet traveller that keeps appearing at the centre of the story. Light has been acting as a guide without making much noise about it, setting limits, defining connections, and revealing how the universe keeps its own sense of order. Now it feels like the right moment to look at it more closely, not as a background constant, but as a physical thing with its own strange and surprisingly rich nature. At first, light seems familiar. You switch on a lamp, the room brightens. You step outside during the day, and the world reveals its colours and shapes. For most of human history, light was treated as something almost magical, a presence that simply was, without much concern for how it worked. But as physics grew more precise, light became one of the most deeply studied phenomena in science, and in doing so, it revealed a personality that is far more complex than anyone first expected. One way to begin is by thinking about light as a wave. This idea emerged in the 19th century, when scientists like James Clerk Maxwell brought together electricity and magnetism into a single unified framework. Maxwell showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. When these two keep generating each other, the result is a self-sustaining ripple that can travel through space. That ripple is what we call an electromagnetic wave. In this picture, light is not a stream of tiny objects flying through empty space. It is a pattern, a rhythm in the electromagnetic field itself. The electric and magnetic parts of the field oscillate, rising and falling in a steady dance as the wave moves forward. The speed at which this pattern travels is set by fundamental properties of space, the electric permittivity and magnetic permeability of the vacuum. When Maxwell calculated that speed, he found it matched the known speed of light. This was a quiet but powerful moment. It suggested that light itself is an electromagnetic phenomenon, not something separate. This wave picture explains a lot about how light behaves. It accounts for reflection, where light bounces off surfaces at predictable angles. It explains refraction, where light bends as it passes from one medium to another, like air into water. It makes sense of interference patterns, where two beams of light overlap and create regions of brightness and darkness, not because the light disappears, but because the waves add together or cancel each other out. You can see this kind of behaviour in simple experiments, like shining light through two narrow slits and watching the pattern it creates on a screen behind them. Instead of forming two bright spots, the light spreads out into a series of alternating bands. This is exactly what you would expect from waves that can overlap and interfere with themselves. For a long time, this wave description seemed complete. Light was a vibration, a travelling oscillation in an invisible field. But then, in the early 20th century, a series of experiments began to show that this was not the whole story. One of the most striking of these involves something called the photoelectric effect. When light shines on a metal surface, it can knock electrons loose, causing a small electric current to flow. Classical wave theory predicted that the energy of the light should depend on its brightness. Make the light brighter, and the waves should carry more energy, eventually kicking electrons out no matter what colour the light is. But what scientists observed was different. Below a certain frequency, no amount of brightness would free any electrons at all. Above that frequency, even very dim light could do the job. It was as if the energy of the light was tied not to how intense the wave was, but to its colour, its frequency. Albert Einstein offered an explanation that pushed physics in a new direction. He suggested that light does not deliver its energy as a smooth, continuous wave. Instead, it arrives in discrete packets, little bundles of energy that we now call photons. Each photon carries an amount of energy that depends on the frequency of the light. Higher frequency means more energy per photon. In this view, shining light on a metal is like throwing a stream of tiny balls at a surface. If the balls are energetic enough, they can knock electrons free. If they are not, no amount of extra balls will help. You can throw as many low-energy photons as you like, but if each one is below the threshold, nothing happens. This particle-like behaviour of light was not a small adjustment. It forced physicists to accept that light cannot be described purely as a wave or purely as a particle. It is, in some sense, both. Depending on how you look at it and what you ask it to do, it will behave like a spreading wave or like a stream of discrete messengers. This dual nature is one of the central features of quantum physics. It is not just light that behaves this way. Electrons, protons, and even entire atoms can show wave-like behaviour under the right conditions. But light is often the first place people encounter this strange blend of identities. To make sense of this without getting lost in abstraction, it can help to think about what light actually does. At its core, light is how the electromagnetic field changes and carries those changes from one place to another. When an electron in an atom shifts from one energy level to another, it disturbs the electromagnetic field. That disturbance propagates outward. At the same time, the energy involved in that change is not spread out smoothly. It is delivered in a quantized amount, a photon. So you can picture light as a kind of travelling event. It is a ripple in a field, but also a package of energy and momentum moving from a source to a receiver. This brings us back to the idea of light as a messenger. When something happens somewhere in the universe, light is often how you find out about it. The glow of a star, the flash of a lightning strike, the gentle warmth of the sun on your skin, all of these are information carried by photons that left their sources and travelled through space to reach you. Every photon carries with it a small story. It encodes the energy change that created it. It carries a direction of travel. It can even carry information about the environment it passed through, such as the presence of magnetic fields or interstellar dust that altered its path or polarization. From this perspective, the universe is constantly sending messages to itself, and light is one of the primary couriers. The speed at which those messages travel is the speed of light, and that speed sets the tempo for how quickly different parts of the cosmos can stay in touch. The wave aspect of light helps explain how these messages spread out and interact. The particle aspect helps explain how they deliver energy and trigger specific, localized events, like an electron jumping to a higher energy level in a detector, or a chemical reaction starting in your eye that leads to the sensation of sight. Richard Feynman had a particular way of talking about this. He often emphasized that what we observe is not light itself in some pure, isolated form, but the interaction between light and matter. We never see a photon in mid-flight. We see it when it's created, and we see it when it is absorbed. Everything in between is inferred. This is where his path integral approach offers an interesting picture. In this framework, a photon does not take a single, well-defined path from its source to its destination. Instead, it explores all possible paths, and the ones that matter are the ones where the contributions line up in a way that reinforces each other. The result is the path that looks like the straight line you would draw in a simple diagram. You do not need to follow the mathematics of this to appreciate the idea. What it suggests is that light's behaviour is not about choosing a single route, but about the combined effect of many possibilities. The wave-like interference patterns and the particle-like detection events are two sides of this same underlying process. This also helps connect light's dual nature to the structure of space-time we have been talking about. The paths that photons explore are paths through space-time. The speed of light defines which paths are even allowed. A photon's journey traces out a line that always stays on the boundary of what is causally connected, never dipping inside the region where slower, massive objects move, and never stepping outside into the region where cause and effect would lose their meaning. Another way to see this is to consider the fact that, from the photon's own perspective, time does not pass in the usual way. This is a subtle and sometimes misleading idea, but it points to something real. The proper time along a light-like path is 0. In the language of relativity, that means there is no passage of time experienced along the path of a photon. This does not mean that a photon has a consciousness or an experience. It means that the space-time interval along its path is fundamentally different from the interval along the path of a massive object. Light does not age. It does not carry a clock that ticks. It simply connects one event to another, creation to absorption, without any internal notion of duration. This makes light a kind of bridge in space-time. It links moments and places in a way that nothing else does. Massive objects always move within the interior of the light cone, always carrying their own time forward with them. Light rides the edge, defining the boundary. This boundary role is part of why light appears so deeply in the laws of physics. It is not just another thing in the universe. It is a structural feature of how the universe is organized. Now, consider what happens when light interacts with matter. When a photon meets an electron, it can be absorbed, transferring its energy to the electron. The electron might jump to a higher energy state, or it might be ejected entirely from an atom. When an electron drops back down to a lower energy state, it can emit a photon, sending energy back out into the electromagnetic field. This constant exchange is happening everywhere, all the time. The warmth you feel from a heater is photons being absorbed by molecules in your skin, increasing their motion. The image you see when you look at a screen is photons triggering chemical changes in the cells of your retina. Even the solidity of objects is, at a deeper level, tied to electromagnetic interactions. The forces that keep atoms from collapsing into one another, and that give materials their rigidity, are rooted in the same field that light is a part of. So light is not just a visitor passing through a universe made of other things. It is woven into the very fabric of how matter holds itself together and how energy moves from one place to another. This perspective also sheds light on why the speed of light appears in places where you might not expect it. It shows up in equations describing electricity and magnetism. It appears in formulas for energy and mass. It even enters into the structure of space-time itself. The electromagnetic field and space-time are not separate realms that happen to overlap. They are deeply connected. The way the field propagates defines the causal structure of space-time, and the geometry of space-time influences how the field propagates. This mutual relationship becomes especially clear when you consider gravity. In general relativity, gravity is described as a curvature of space-time caused by mass and energy. Light follows that curvature. Its path bends near massive objects, not because it is being pulled like a rock on a string, but because the geometry of space-time itself is curved. This bending of light has been observed in phenomena like gravitational lensing, where the light from a distant galaxy is distorted and magnified by the gravity of a massive cluster of galaxies in between. The photon's role as a messenger becomes even more dramatic here, as it carries with it not just information about its source, but also a record of the space-time it travelled through. In this sense, every photon that reaches you is a kind of map. It tells a story about where it came from and what it encountered along the way. Its direction, its energy, its polarization, all carry clues about the universe beyond your immediate surroundings. This brings a certain quiet depth to the simple act of looking. When you gaze at a distant star, you're not just seeing a point of light. You're receiving a stream of photons that left that star years, centuries, or even millions of years ago. You are, in a very real sense, looking into the past. The wave-particle duality of light does not disappear in this larger context. It becomes part of how these messages are encoded and delivered. The wave aspect governs how the light spreads, interferes, and bends. The particle aspect governs how it deposits energy and triggers specific events when it arrives. Feynman's diagrams provide a way to visualize this exchange. A wavy line represents a photon travelling between 2 points, where charged particles interact. At one end, an electron emits a photon. At the other, another electron absorbs it. The line in between is not a literal picture of a tiny ball flying through space. It is a representation of a process, a way of accounting for how energy and momentum are transferred according to the rules of quantum electrodynamics. What is remarkable is how well this abstract bookkeeping matches reality. The predictions made using these diagrams agree with experiments to an astonishing degree of precision. The theory of how light and matter interact is one of the most accurate scientific frameworks ever developed. This accuracy suggests that the strange dual nature of light is not a temporary confusion waiting to be resolved into something simpler. It may be a fundamental feature of how the universe works. The world at its deepest level does not divide neatly into waves and particles. It uses a language that includes aspects of both. As you sit with this, it can be helpful to let go of the urge to pin light down as one thing or the other. Instead, think of it as a process, an interaction, a way that change moves through the electromagnetic field and connects one event to another. This way of thinking also fits naturally with the role light plays in setting the limits on speed and causality. It is not just a fast object. It is the mechanism by which the universe keeps track of itself. Every signal, every influence, every exchange of information is ultimately constrained by how disturbances in fields propagate. Light is the most direct expression of that propagation. It becomes clear that understanding light is not just about understanding illumination or radiation. It is about understanding how the universe communicates, how it maintains order, and how it draws the line between what can be connected and what remains out of reach, at least for now. At a certain point in this gentle walk through light and motion, it becomes clear that the story is not just about what moves or how fast it moves, but about who is doing the measuring. Every statement about speed, distance, or time quietly depends on a point of view, a place from which the universe is being observed. This is where the idea of a reference frame steps in, not as a technical tool meant only for textbooks, but as a simple and deeply human way of asking, from where am I seeing this? In everyday life, you use reference frames without ever naming them. When you say that a cup is sitting still on a table, you mean it is still relative to the room around it. When you say that a car is moving down the street, you mean it is moving relative to the ground beneath your feet. You do not usually worry about the fact that the Earth itself is spinning, or that the planet is orbiting the Sun, or that the Sun is circling the centre of the galaxy. Those large emotions are there, but they fade into the background of your chosen point of view. Physics takes this everyday habit and turns it into a formal idea. A reference frame is simply a way of labelling where and when things happen. It is a set of rulers and clocks, real or imagined, that an observer uses to assign coordinates to events in space and time. Once you choose a frame, you can say this happened here, at this time, and start building a description of how things move and interact. For a long time, scientists believed there was a special, universal reference frame hiding behind all the others. In this view, space and time were absolute. There was a true cosmic clock ticking away somewhere in the background, and all the individual clocks carried by moving observers were just imperfect copies of that deeper, universal time. If you could somehow strip away all motion and all perspective, you would find the real version of what is happening when and where. This idea fit neatly with how the world seemed to behave at ordinary speeds. Whether you were standing still or riding in a carriage, the same physical laws appeared to apply. Objects fell to the ground. Water flowed downhill. Pendulums swung back and forth. The details might change, but the basic rules did not. It felt natural to imagine that there was a single, solid stage behind it all. The shift away from this picture began quietly, with a simple but stubborn observation. No matter how you move, no matter how fast or in what direction, the speed of light always comes out the same when you measure it. This was not what classical ideas about reference frames would predict. If you were moving toward a light source, you should measure the light as moving faster. If you were moving away, you should measure it as moving slower. But experiment after experiment refused to show any such change. This forced a choice. Either the idea of a universal reference frame had to go, or the idea that the speed of light was truly constant had to be given up. Physics chose to keep the light. The result was a new way of thinking about reference frames. Instead of there being one special frame that defines reality, all frames that move at constant velocities relative to one another are placed on equal footing. These are called inertial frames, and in each one, the laws of physics take the same form. No experiment done entirely within such a frame can tell you whether you are really at rest or really moving. Motion becomes relative, not absolute. This idea is sometimes called the principle of relativity. It does not mean that everything is subjective or that reality depends on opinion. It means that the fundamental rules of nature do not pick a favourite point of view. They work the same way for everyone who is not accelerating. To see how this plays out, imagine you are sitting in a train that is moving smoothly along a straight track at a constant speed. The windows are closed. The ride is so steady that you cannot feel any vibration or sway. Inside the train, you drop a ball. It falls straight down to the floor at your feet. You toss it up, and it comes back down into your hand. Now imagine someone standing on the platform outside watching the train pass by. From their perspective, when you drop the ball, it follows a curved path, moving forward with the train while also falling downward. Both of you see the same physical event, but you describe it differently because you are using different reference frames. What is remarkable is that the underlying laws that describe the ball's motion work in both frames. The equations of physics take the same form. You do not need to add special corrections just because you are on a moving train. This symmetry is what makes reference frames such a powerful idea. It tells you that physics is not about finding the one true viewpoint. It is about finding rules that work in all viewpoints. When light enters the picture, this symmetry becomes even more striking. If you turn on a flashlight inside the moving train, you see the beam travel away from you at the speed of light. The person on the platform also sees that beam travel at the speed of light, even though from their perspective the train is moving. Both of you agree on that number, even though you disagree about distances and times. This agreement is not a coincidence. It is built into the structure of space-time. The price of this agreement is that space and time themselves become flexible. To keep the speed of light the same for everyone, different observers must measure different lengths and different durations. A meter stick on the moving train looks shorter to the person on the platform. A clock on the train ticks more slowly from the platform's point of view. These effects are not illusions. They are not caused by faulty instruments or human error. They are real changes in how space and time are experienced in different frames. What remains unchanged across all these shifting measurements are the deeper relationships between events. The laws that govern how energy and momentum are conserved, how charges interact, how particles transform and decay, keep the same form in every inertial frame. This is what gives the title of calm rules that never change its meaning. While distances stretch and time slow, the structure of the laws themselves remain steady. One way to express this steadiness is through something called invariance. An invariant is a quantity that stays the same no matter which reference frame you use to measure it. In classical physics, time was invariant. Everyone agreed on how much time passed between two events. In relativity, time is no longer invariant. Instead, a different quantity takes its place. This new invariant is the space-time interval, a combination of space and time measurements that remains the same for all observers, even though they may disagree on the individual pieces. It is a way of measuring the distance between two events in space-time, not just in space or just in time, but in the combined four-dimensional structure. You do not need to work through the formula to appreciate the idea. What matters is that there is still something solid beneath the shifting perspectives. Even though one observer might say two events are far apart in space and close together in time, and another might say they are closer in space and farther apart in time, they will both agree on the value of this combined space-time separation. This shared quantity is what keeps the universe coherent. It ensures that all observers, no matter how they move, are still describing the same underlying reality. Light plays a special role here because the space-time interval along a light-like path is always zero. This is another way of saying that light defines the boundary between different kinds of separations in space-time. Events connected by light sit right on the edge of what can influence what. This brings us back to causality, the idea that causes come before effects. In a universe where reference frames can disagree about time order, causality might seem fragile, but the structure defined by light keeps it safe. If one event can influence another, there is a light speed or slower path connecting them. That path ensures that all observers will agree on which one happened first. Reference frames may shuffle the labels of now and then, but they cannot turn an effect into a cause. The calm rule that cause precedes effect remains unchanged. Richard Feynman often enjoyed pointing out that this is one of the great triumphs of modern physics. The rules are subtle, and the perspectives are many, but the universe does not descend into chaos. There is a deep consistency that holds everything together. He liked to describe physics as a game where you try to figure out the rules by watching how nature behaves. The beauty, he said, is not just in the rules themselves, but in the fact that they are the same everywhere you look. Reference frames are part of that game. They remind you that your own point of view is just one of many, and that the laws you uncover should not depend on the particular seat you happen to be sitting in. This idea extends beyond motion at constant speeds. When you start to consider accelerating frames, things get even more interesting. If you are in a car that is speeding up, you feel pushed back into your seat. If you are in an elevator that is starting to rise, you feel heavier. These sensations are clues that something has changed. You can now perform experiments inside your frame that tell you are accelerating. Einstein took this observation and turned it into a powerful insight. He noticed that the effects of acceleration and the effects of gravity feel remarkably similar. Standing in an accelerating elevator feels a lot like standing in a gravitational field. This led him to propose that gravity itself is not a force in the usual sense, but a feature of curved space-time. In this view, reference frames become even more flexible. Observers in different gravitational fields or different states of acceleration experience space and time in different ways. Clocks tick at different rates depending on how deep they are in a gravitational well. Light bends as it passes near massive objects, following the curved geometry of space-time. And yet, even here, the calm rules persist. The fundamental equations that describe how space-time curves and how matter and energy move within that curvature take the same form in every frame. The math becomes more complex, but the principle of relativity remains. This universality is one of the reasons the speed of light remains such a central figure. It appears not just as the speed of electromagnetic waves, but as a conversion factor between space and time in the geometry of space-time itself. It sets the scale for how these two aspects of reality are related. In many modern formulations of physics, units are chosen so that the speed of light is simply set to 1. In these units, space and time are measured in the same terms. The distinction between them becomes a matter of direction in space-time rather than a difference in kind. This is a mathematical choice, but it reflects a deep physical truth. Space and time are two sides of the same coin. From this angle, reference frames are ways of slicing that coin differently. One observer's space is another observer's mix of space and time. One observer's now is another observer's not quite yet, or just happened. What holds all these slices together is the invariant structure beneath them, the space-time intervals, the light cones, the conservation laws, and the unchanging form of the equations. This structure gives physics its quiet stability. Even as perspectives shift, even as measurements stretch and shrink, the relationships that matter most remain in place. There is something gently reassuring about that. It suggests that the universe is not a patchwork of disconnected viewpoints, but a single, coherent whole that can be described in many ways without losing its underlying order. As you move through your own day or night, you carry your own reference frame with you. Your clocks tick at your own pace. Your rulers measure distances in your own surroundings. And yet, without you ever noticing, your measurements fit seamlessly into this larger structure that connects you to distant stars, moving galaxies, and the faint glow of ancient light crossing the vastness of space. This quiet harmony between the local and the cosmic is part of what makes the idea of reference frames so powerful. It ties your personal experience of motion and rest to the deepest laws of nature. Somewhere in the quiet space between all these shifting viewpoints and steady rules, there is a single, almost modest statement that changed the entire shape of physics. It does not arrive with dramatic flair or complicated language. It simply says that the speed of light in a vacuum is the same for all observers, no matter how fast they're moving or in what direction. This idea, often called Einstein's postulate, sounds gentle enough when you first hear it. Yet from this one sentence flows an entire universe of consequences, including the very notion that there must be a universal speed limit woven into the fabric of reality. To appreciate why this mattered so much, it helps to step back into the world of physics as it existed at the end of the 19th century. At that time, scientists had a remarkably successful picture of how forces and motion worked. Newton's laws describe the movement of planets and cannonballs with equal confidence. Maxwell's equations unified electricity, magnetism, and light into a single, elegant framework. The industrial world was running on these ideas, building engines, telegraphs, and power systems that reshaped daily life. And yet, hidden within this success was a quiet tension. Maxwell's equations predicted that electromagnetic waves, including light, travel at a specific speed determined by the properties of space itself. This speed did not depend on the motion of the source or the observer. It was just there, a fixed number that dropped out of the math. This was strange because it did not fit neatly into the older classical idea of how reference frames worked. In that older view, speeds always added. If you ran toward a moving train, you would meet it faster than if you stood still. If you were moving away, it would take longer to reach you. There was no reason to think light should be any different. To make sense of this, many physicists assumed that light must be travelling through some kind of invisible medium, often called the luminiferous ether. This ether was imagined as a substance that filled all of space, providing a reference frame relative to which light's true speed could be measured. If the Earth moved through this ether, then careful experiments should be able to detect that motion by measuring small changes in the speed of light in different directions. One of the most famous attempts to do this was the Michelson-Morley experiment. Using a clever arrangement of mirrors and light beams, they tried to measure differences in the speed of light caused by the Earth's motion through the supposed ether. If the ether existed, the light travelling along the direction of Earth's motion should take a different amount of time than the light travelling perpendicular to it. The result, again and again, was silence. No difference appeared. The speed of light seemed stubbornly the same in all directions, no matter when or where the experiment was performed. This left physicists with a choice. They could keep the idea of an ether and invent increasingly complicated explanations for why it could not be detected, or they could let go of the ether and take the constancy of the speed of light seriously. Albert Einstein, working as a patent clerk and thinking deeply about the nature of time and motion, chose the second path. In 1905, he published a paper that began with two simple postulates. The first was the principle of relativity, which said that the laws of physics are the same in all inertial reference frames. The second was the statement about the speed of light, that it is constant for all observers, regardless of their motion. He did not try to explain why this was true. He simply took it as a fact about the world and asked what must follow if it is. The answers were both surprising and elegant. If the speed of a light is truly the same for everyone, then measurements of space and time cannot be absolute. They must adjust to preserve that constancy. This is where the idea of a universal speed limit begins to take on a deeper meaning. It is not that light happens to be the fastest thing around. It is that the structure of space-time itself is built in such a way that no signal, no object, and no influence can outrun the way light connects events. From Einstein's postulate, time dilation follows naturally. Consider two observers, one standing still and one moving at a constant speed. Each carries a clock. According to classical ideas, those clocks should tick at the same rate. But if both observers measure the speed of light and get the same result, then their measurements of time and distance must differ. The moving clock ticks more slowly when seen from the stationary frame. This is not a mechanical effect like a watch being shaken. It is a fundamental change in how time itself is measured between frames. Length contraction follows in a similar way. An object moving relative to an observer is measured to be shorter along the direction of motion. Again, this is not because the object is being physically squashed. It is because the observer's definition of simultaneous events along the object's length has changed. Together, these effects ensure that when distances are divided by times to calculate speed, the result for light always comes out the same. What emerges from this is a kind of cosmic bookkeeping. The universe keeps the speed of light fixed by letting space and time themselves be flexible. As one stretches, the other compensates. Now, consider what happens when you try to accelerate an object. At low speeds, adding energy increases its velocity in a way that feels familiar. But as the object's speed approaches that of light, the relativistic effects become stronger. Time dilation increases, length contraction becomes more pronounced. The energy required to produce even a small increase in speed grows larger and larger. Mathematically, this shows up in the expression for relativistic energy and momentum. The factor that multiplies mass and velocity includes a term that approaches infinity as the velocity approaches the speed of light. Physically, this means that reaching the speed of light would require an infinite amount of energy. This is the heart of the universal speed limit. It is not enforced by a barrier or a force that pushes back when you get too fast. It is enforced by the way energy, space, and time are related. The closer you get to the limit, the more the cost of moving closer increases without bound. Light itself does not face this problem because it does not have mass. Photons always move at the speed of light. They cannot go slower, and they cannot go faster. Their energy is expressed not as kinetic energy in the usual sense, but through their frequency. Higher energy photons have higher frequencies, not higher speeds. This again highlights how different light is from ordinary matter. Matter lives inside the light cone, always moving more slowly than the boundary defined by light. Light lives on the edge, defining that boundary. Richard Feynman often enjoyed pointing out that this single postulate, the constancy of the speed of light, acts like a seed from which a whole forest of physical laws grows. It reshapes how you think about motion, energy, mass, and even the concept of simultaneity. One of the more subtle consequences of Einstein's postulate is the relativity of simultaneity. In classical thinking, there is a universal now that stretches across the entire universe. Events that happen at the same time for one observer happen at the same time for all observers. In relativistic thinking, this is no longer true. Two observers moving relative to each other can disagree about whether two distant events occurred at the same moment. This is not because one of them is mistaken. It is because their definitions of what it means for two events to be simultaneous depend on how they are moving. This might sound abstract, but it has concrete implications. It means that there is no single, global present moment that everyone shares. Instead, each observer carries their own slice of space-time that they call now. Despite this, causality remains intact. Events that can influence each other, connected by signals travelling at or below the speed of light, will always maintain the same order for all observers. The universal speed limit ensures that cause and effect cannot be reversed by changing reference frames. This balance between flexibility and structure is one of the most striking features of Einstein's framework. Time and space can bend and shift, but the core relationships that keep the universe consistent remain fixed. The idea of a speed limit also extends beyond light itself. It applies to all forms of information. You cannot send a message, flip a switch, or trigger a reaction in a distant place faster than light can travel between the 2 points. This is not a technological limitation. It is a fundamental property of how space-time is organized. Even in the strange world of quantum mechanics, where particles can become entangled and show correlations across vast distances, this limit holds. Entanglement does not allow usable information to be transmitted faster than light. The correlations appear instantly, but no signal, no controllable message can outrun the light boundary. This preserves the same causal structure that Einstein's postulate enforces. The universe may allow for deep and subtle connections, but it does not allow for contradictions in the order of cause and effect. Another way to see the importance of this speed limit is to consider how it shapes the large-scale structure of the cosmos. The finite speed of light means that the observable universe is limited. There are regions of space so far away that their light has not had time to reach us since the beginning of cosmic expansion. These regions exist, but they lie beyond our current horizon. This horizon is not a physical wall. It is a boundary in time. It marks the limit of how far back we can see and how far out we can be influenced by. As the universe expands, this horizon changes. New regions come into view as their light finally has time to reach us. Others move out of reach as the expansion of space itself carries them away faster than light can bridge the gap. Here, the speed of light interacts with the expansion of space in a subtle way. While nothing can move through space faster than light, space itself can expand in such a way that distant galaxies recede from us at an effective rate greater than the speed of light. This does not violate Einstein's postulate, because the galaxies are not moving through space faster than light. The space between us and them is growing. Even in this more complex picture, the speed of light remains the local limit. It governs how signals and influences propagate from one point to another, even as the larger scale structure of space evolves. The universality of this limit has practical consequences in technology as well. Systems like GPS rely on precise timing signals sent from satellites to receivers on Earth. Those signals travel at the speed of light, and the relativistic effects of both motion and gravity have to be accounted for to maintain accuracy. Without Einstein's corrections, GPS positions would drift by kilometers each day. This is a quiet reminder that these ideas are not just philosophical or theoretical. They are woven into the tools you use to navigate the world. Richard Feynman often emphasized the importance of respecting what experiments tell you, even when the results seem strange. The speed of light's constancy is one of those experimental facts that forces you to rethink your intuitions. He liked to point out that nature is not obligated to make sense in terms of everyday experience. Our intuitions are shaped by a world of slow speeds and gentle motions. When you step outside that world, into realms of extreme velocity or tiny scales, the rules change, and you have to let the evidence guide you. Einstein's postulate is a perfect example of this. It takes a simple measurement, the speed of light, and elevates it to a principle that reshapes the entire framework of physics. From this principle, the idea of a universal speed limit emerges not as an arbitrary rule, but as a natural consequence of how space and time are stitched together. It is worth pausing to notice how economical this is. Instead of adding new forces or constraints, the universe uses the geometry of space-time itself to enforce its limits. The rules are built into the way distances and durations relate to one another. This elegance is part of what makes the theory so satisfying. A single postulate leads to a network of results that all fit together, from time dilation and length contraction to energy mass equivalence and the structure of causality. As you let this idea settle, it can be helpful to think of the speed of light not as a barrier, but as a scale. It is a number that tells you how space and time convert into each other. It is the factor that turns seconds into meters and meters into seconds in the deep equations of the universe. In this sense, the universal speed limit is also a universal translator. It allows different observers with different clocks and rulers to speak the same physical language, somewhere between the steady rules that keep the universe consistent and the restless motion of particles that fill every corner of space. There is a way of thinking that feels less like a list of equations and more like following a set of quiet journeys. Richard Feynman had a talent for seeing physics not as a static collection of facts, but as a story about things moving, interacting, and leaving subtle traces of their passage behind. When he spoke about particles, he often described them not as tiny, solid beads drifting through empty space, but as travellers tracing paths through space-time itself, each one following a route shaped by the same deep limits and connections that light reveals. To begin easing into this idea, it helps to let go of the picture of a particle as a little dot that exists at a single point and then hops to another point in the next moment. Instead, imagine the particle as something that leaves behind a continuous line, a kind of thread woven into the fabric of space-time. That thread is its history. It records where the particle has been and when it was there. Physicists call this thread a world line, and it is one of the simplest, most powerful ways to visualize motion in a relativistic universe. In this picture, space-time becomes a vast map, and every particle draws its own path across it. A particle at rest draws a line that goes straight upward through time, staying in the same place in space. A particle in motion draws a slanted line, moving forward in time while also shifting through space. Light draws a line that sits at a special angle, right on the boundary of what is allowed, marking the edge between what can be causally connected and what cannot. Feynman found this way of thinking appealing because it made abstract ideas tangible. Instead of talking about changing positions and ticking clocks, you could talk about paths and intersections. When two particles interact, their world lines meet. When a particle decays into others, one line splits into several. When energy is exchanged, the geometry of these lines reflects that transfer. This approach becomes especially clear in what are now called Feynman diagrams. At first glance, these diagrams look almost too simple, like sketches drawn in the margin of a notebook. Lines meet at points, split apart, or exchange wavy connectors. But behind these simple drawings is a precise mathematical language that encodes how particles interact according to the rules of quantum field theory. In these diagrams, time usually runs in one direction across the page, and space runs in another. A straight line might represent an electron travelling from one moment to the next. A wavy line might represent a photon carrying energy and momentum between two charged particles. The points where the lines meet represent interactions, moments when something happens, when a particle emits or absorbs another particle. What makes this representation so powerful is not just that it simplifies calculations, but that it reinforces the idea of particles as travellers. Each line is a journey. Each vertex where lines meet is a meeting place, an exchange, a brief conversation between different parts of the universe. Now, beneath this neat visual language lies a deeper and stranger idea that Feynman introduced through his path integral formulation of quantum mechanics. Instead of assuming that a particle takes a single, well-defined path from its starting point to its destination, he proposed that it takes all possible paths. This does not mean that a particle literally splits into copies and wanders every route like a curious explorer. It means that when you calculate the probability of a particle going from one place to another, you have to consider contributions from every possible path it could take, even the wildly indirect and seemingly unreasonable ones. Each of these paths contributes a kind of tiny arrow, a complex number with a direction and a length, and when you add them all together, most of them cancel out. The paths that line up and reinforce each other are the ones that dominate. The result is that, on average, the particle appears to follow a path close to the one you would expect from classical physics, like a straight line in empty space. This idea blends naturally with the picture of world lines in space-time. Instead of a single, crisp thread, a particle's journey becomes a kind of cloud of possibilities, all woven together into the final, observed path. What makes this especially interesting in the context of a universal speed limit is that all of these possible paths still respect the structure of space-time. They all lie within the region allowed by the speed of light. None of them jump outside the light cone to connect events that should not be causally linked. In this way, even at the quantum level, where uncertainty and probability rule, the deeper geometry of space-time still sets the stage. Feynman liked to emphasize that what we actually observe in experiments are not the paths themselves, but the endpoints. We see where a particle is created, and we see where it is detected. Everything in between is inferred. The path integral approach is a way of systematically accounting for that inference. This brings a certain humility into the picture. Instead of claiming to know exactly what a particle is doing at every moment, the theory admits that there are many possibilities, and what we can predict are the probabilities of different outcomes. Now, consider how this view connects to the idea of particles carrying energy and momentum through space-time. In classical thinking, a particle is like a little billiard ball. It has a position, a velocity, and a trajectory. In quantum field theory, a particle is more like a localized excitation in a field, a small ripple that moves and interacts. The electron is not just a dot. It is an excitation in the electron field. The photon is not just a tiny bullet of light. It is an excitation in the electromagnetic field. These fields fill all of space, even in regions that seem empty. In this picture, particles travelling through space-time are really patterns of activity in these underlying fields. The world line you draw in a diagram is a way of tracking where that activity is concentrated over time. This shift in perspective helps explain why interactions look the way they do in Feynman diagrams. When an electron emits a photon, it is not throwing a tiny object across space like a baseball. It is disturbing the electromagnetic field, creating a ripple that propagates outward and can later interact with another charged particle. The diagram captures this by drawing a wavy line connecting 2 points on 2 electron lines. It is a visual shorthand for a much richer process. Another subtle feature of these diagrams is that they do not always respect our everyday sense of time in a simple way. Sometimes lines in a Feynman diagram are drawn as if a particle is moving backward in time. This does not mean that particles literally travel into the past. It is a mathematical way of representing certain kinds of interactions, such as the behaviour of antiparticles. In this language, an antiparticle can be thought of as a particle moving backward through time. This is not a literal statement about causality, but it is a useful way to encode how particles and antiparticles are related in the equations. This idea fits surprisingly well with the space-time picture. Instead of thinking of particles as things that exist only in space, you think of them as patterns in space-time that can have different orientations. A line slanting one way represents a particle. A line slanting the other way can represent an antiparticle. What remains consistent through all of this is the role of the speed of light as the boundary. Even in these abstract diagrams, the allowed paths and interactions respect the same causal structure. Energy and information do not jump across space-time in ways that would violate the light limit. Feynman's approach also brings attention to the role of probability in these journeys. When you look at a single particle travelling from one point to another, you cannot predict its exact path. You can only predict the likelihood of different outcomes. This probabilistic nature does not come from ignorance or lack of precision. It is built into the way the universe works at small scales. The path integral formulation makes this explicit by treating every possible path as part of the calculation. What you observe in the end is the result of many possibilities combining, interfering, and reinforcing each other. Now, place this picture back into the larger framework of space-time and reference frames. Each observer, in their own frame, can draw their own version of a particle's world line. The coordinates may differ, the slopes may look different, but the underlying relationships between events remain the same. If two particles interact in one frame, they interact in all frames. If a particle decays at a certain point in space-time, that event is the same event for everyone, even if they assign it different times and positions. This invariance of events is what allows Feynman diagrams to work as a universal language. Physicists in different frames can use the same diagram and get the same physical predictions. Another interesting feature of Feynman's view is how it treats virtual particles. In the diagrams, not every line represents a particle that can be directly observed. Some lines represent virtual particles, temporary disturbances in a field that exist only as part of an interaction. These virtual particles do not obey the same simple relationships between energy, momentum, and speed that real, observable particles do. They can appear to borrow energy for a brief moment, as long as they give it back quickly enough, according to the uncertainty principle. This might sound like a loophole in the universal speed limit, but it is not. Virtual particles are not things you can send messages with. They are part of the internal bookkeeping of interactions, not carriers of usable information. The overall process, when taken as a whole, still respects causality and the speed of light. In this sense, the path integral and the diagrammatic approach provide a kind of internal view of how the universe manages its interactions. They show you the hidden complexity behind even the simplest exchange of energy. Think, for example, about two electrons repelling each other. In classical terms, you might say they push each other away through the electric force. In the language of quantum electrodynamics, you draw two electron lines exchanging a photon. That photon is virtual. It does not appear in a detector, but it represents the way the electromagnetic field mediates the interaction. The diagram captures the idea that the force is not a direct, instantaneous push. It is an exchange process that unfolds in space-time, constrained by the same rules as everything else. This brings us back to the idea of particles as travellers. Even when nothing seems to be happening, when two charges are just sitting near each other, there is a constant exchange of virtual photons, a quiet traffic of interactions that maintains the force between them. Space-time, in this view, is never truly empty. It is a stage filled with potential, with fields ready to ripple and interact. Feynman often emphasized that what we call particles are really just convenient ways of talking about what fields are doing. The electron is a particular pattern in the electron field. The photon is a particular pattern in the electromagnetic field. Their journeys are patterns of activity moving through space-time. This field-based view helps explain why the speed of light is so central. It is not just the speed of a particular kind of particle, it is the speed at which changes in fields propagate. No matter which field you look at, electromagnetic, gravitational, or even the more abstract fields of the quantum world, there is a characteristic speed at which disturbances move. For the electromagnetic field, that speed is the speed of light. For the gravitational field, changes also propagate at the speed of light. This means that when a massive object moves, the information about that motion, the change in the gravitational field, does not reach distant regions instantly. It travels outward at the same universal pace. So in Feynman's picture, particles travelling through space-time are always embedded in a web of fields that communicate changes at a finite speed. Their journeys are not isolated. They are part of a network of interactions that extends across the universe. This network is what maintains the calm, steady rules that never change. It is what keeps energy and momentum conserved, what ensures that cause comes before effect, and what preserves the structure defined by the speed of light. Another way to see this is to think about the role of symmetry. The laws of physics have certain symmetries, meaning they look the same under different transformations, like shifting everything in space or time, or rotating a system. These symmetries are deeply connected to conservation laws. For example, the symmetry of the laws under shifts in time is related to the conservation of energy. The symmetry under shifts in space is related to the conservation of momentum. Feynman's diagrams respect these symmetries. The way lines meet and exchange reflects the underlying conservation laws. Energy and momentum flow along the lines, and the points where they meet are constrained by the requirement that these quantities balance. This again reinforces the idea that particles are not just moving through a pre-existing stage. They are participating in a structured dance governed by deep, universal rules. As you let this view settle in, the picture of the universe becomes less like a collection of solid objects moving around in empty space, and more like a living tapestry of interactions, with threads of energy and information weaving through space-time. Each particle's journey is a small part of that tapestry. Each interaction is a knot or a crossing point where threads meet and exchange. The speed of light in this tapestry is like the tension in the threads. It sets how quickly a ripple can travel, how fast a pattern can change, how soon one part of the fabric can respond to another. This perspective does not make the universe feel cold or mechanical. If anything, it adds a kind of quiet richness. Even the simplest event, a single electron drifting through a wire, becomes a story of fields, paths, and exchanges unfolding within a carefully balanced structure. Richard Feynman had a way of bringing this richness to life in his lectures. He would often remind his audience that the more deeply you look into nature, the more surprising and beautiful it becomes, not in a mystical sense, but in the clarity and consistency of its rules. He liked to say that physics is not about finding out what we like to think about nature, but about finding out what nature actually does. His diagrams and path integrals were tools for that discovery, ways of peering into the hidden processes behind the scenes. Far from the familiar feeling of pressing a pedal and watching the world rush by a little faster, there is a quieter and more demanding relationship between motion and effort that only reveals itself when you begin to approach the deeper limits set by space-time. In everyday experience, acceleration feels generous. Push, and something responds. Add a little more push, and it responds a little more. The connection between energy and speed seems almost friendly, as though the universe is happy to cooperate. But beneath that surface simplicity lies a different kind of accounting, one that becomes increasingly strict as motion climbs toward the same steady boundary that light always marks. To ease into this, it helps to think about what energy and momentum mean in the most basic sense. Energy is often described as the capacity to do work, to cause change. Momentum is a measure of motion, combining how much matter something has with how fast it is moving. In the world of slow speeds and familiar forces, these ideas sit comfortably together. If you double the speed of an object, you double its momentum. If you want to make something go faster, you add energy, and the result feels proportional. This relationship is so ingrained in daily life that it can feel almost like a rule of nature, rather than a pattern that holds only under certain conditions. You throw a ball harder, it goes faster. You pedal a bicycle with more effort, it picks up speed. The cause and effect seem clean and direct. What begins to change when you look more closely is not the definitions of energy and momentum, but how they connect to the geometry of space-time itself. As soon as you accept that space and time are woven together, motion becomes something more than just a change of position. It becomes a redistribution of how an object moves through this combined structure. Every object with mass carries its own time forward. Even when it is standing still in space, it is moving through time. When you accelerate it, you're not just giving it motion across the floor or down a track. You're changing the balance between how much it moves through space and how much it moves through time. This trade-off is subtle at low speeds. The shift is so small that it goes unnoticed. The clock carried by a fast-moving object ticks almost in step with a clock at rest. the lengths of moving objects look almost the same as those at rest. In this regime, energy behaves the way you expect. Add a bit and you get a bit more speed. As velocity increases, however, the geometry of space-time begins to assert itself more strongly. Time dilation becomes noticeable. Length contraction becomes measurable. The object's path through space-time tilts closer and closer to the boundary defined by light. Momentum, in this picture, is not just mass times velocity. It is a measure of how strongly an object's world line is tilted away from the time direction and into the space direction. The steeper that tilt, the more momentum the object carries. Energy, meanwhile, is tied to how much an object resists changes to that tilt. When you try to accelerate something, you're trying to rotate its path in space-time to lean it further toward the space direction. The closer it gets to the light boundary, the harder that rotation becomes. This is not because the object develops some kind of magical heaviness. It is because the geometry you are working within becomes increasingly restrictive. There are fewer and fewer directions left to tilt into. Mathematically, this shows up in the factor that connects energy, momentum, and velocity in special relativity. The equations include a term that grows larger and larger as the speed approaches that of light. Physically, this term represents how much more energy you need to achieve a given increase in speed. At first, the growth is gentle. You can still add energy and see a noticeable change in velocity. But as you push closer to the limit, each additional unit of energy produces a smaller and smaller change in speed. The curve flattens out, like a road that becomes steeper and steeper as you climb, until it approaches a vertical wall. This is what is meant by acceleration becoming more costly. The universe does not stop you with a sudden barrier. It simply makes the price of going faster rise without bound. One way to picture this is to imagine trying to move along a surface that becomes more and more slippery as you approach a certain line. At first, your steps carry you forward easily, but as the surface grows slicker, each step produces less forward motion. You have to work harder and harder to make progress, until eventually, no matter how much effort you apply, you cannot cross that line. Energy, in this analogy, is your effort. Speed is your progress. The geometry of space-time is the surface itself. Momentum fits into this picture as a kind of measure of how hard it is to change your motion. The more momentum an object has, the more resistant it is to being pushed into a different path. At low speeds, this resistance is modest. At high speeds, it becomes immense. This is why high-energy particles in accelerators behave the way they do. Scientists can pour enormous amounts of energy into them, yet their speeds change only slightly. Instead of getting much faster, they become much more energetic in a different sense. Their momentum and energy grow, but their velocity creeps closer and closer to the same familiar limit. What changes dramatically is not how fast they go, but how much energy they carry. This energy shows up in other ways, such as in the ability of the particle to create new particles when it collides with something else. Here, the connection between energy and mass comes quietly back into view. Einstein's equation, E equals mc squared, tells you that mass itself is a form of energy. When a particle carries a great deal of energy, it can, under the right conditions, convert that energy into new mass. This is why particle accelerators are sometimes described as mass factories. By accelerating particles to extremely high energies and smashing them together, scientists can create new, heavier particles that did not exist before the collision. In this process, speed plays a curious role. The particles are already moving very close to the speed of light long before they reach the energies needed to create heavy new particles. The extra energy does not go into making them much faster. It goes into increasing the total energy available in the collision. This is another way of seeing how the speed limit shapes the behaviour of the universe. It channels additional energy into new forms rather than into unbounded increases in velocity. Momentum conservation adds another layer to this story. In any isolated system, the total momentum before an interaction must equal the total momentum after. This rule holds in classical physics and in relativistic physics. It is one of those calm, steady principles that remain unchanged even as the details shift. In the relativistic setting, however, momentum is tied more deeply to energy and spacetime geometry. Energy and momentum form a single combined quantity, often called a four-vector, that transforms neatly between reference frames. This means that when you look at an interaction from different points of view, the way energy and momentum are divided among the particles can look different, but the combined structure remains consistent. Feynman diagrams are especially good at capturing this idea. The lines in the diagram carry energy and momentum. At each point where lines meet, the total flow in and out must balance. This is the diagrammatic expression of conservation laws. Even when virtual particles appear in these diagrams, borrowing energy for a brief moment, the overall accounting still works out. The rules are not broken. They're applied in a more subtle, time-limited way that still respects the underlying structure. This brings us back to the idea of cost. When you try to accelerate a particle, you're not just pushing it through space. You're feeding energy into this network of conservation laws, space-time geometry, and field interactions. At low speeds, the network is flexible. It absorbs the energy and produces a noticeable change in velocity. At high speeds, the network becomes rigid. It channels the energy into increased momentum, increased total energy, and, under the right conditions, the creation of new particles. The speed itself remains pinned near the same limit. There is something quietly elegant about this. The universe does not allow energy to pile up in a single, runaway way. It redistributes it, finding new outlets when one path becomes blocked. This redistribution also has a deep connection to time. As a particle's speed increases, the passage of time along its world line slows relative to an external observer. This means that, from the particle's own perspective, less time passes during its journey. This has an interesting consequence for how the particle experiences forces. A force applied over a given interval of external time corresponds to a different interval of the particle's own time. As the particle's time slows, the same force, applied for the same external duration, has a reduced effect on its velocity. This is another way of understanding why acceleration becomes harder. The particle's own clock is running more slowly, so it has less time in its own frame to respond to the push. Again, this is not a mechanical resistance. It is a feature of how time itself is woven into motion. This perspective also helps explain why nothing with mass can ever reach the speed of light. To do so would require not just an infinite amount of energy, but an infinite amount of time in the particle's own frame. The particle would have to be pushed forever, without ever quite reaching the boundary. Light, which does not experience time in the same way, does not face this constraint. Photons move at the speed of light by their very nature. They do not need to be accelerated to get there. They are born on the boundary. This distinction between massive particles and massless ones is another quiet thread running through the structure of physics. It shows up in how energy and momentum are related, in how world lines are shaped, and in how interactions unfold. Now consider what this means for the idea of force. In classical physics, a force produces an acceleration according to a simple rule. In relativistic physics, that rule still holds in a local sense, but the relationship between force and the resulting change in velocity becomes more complex at high speeds. The same force can produce a smaller and smaller change in velocity as the speed increases. Instead, it produces a larger change in energy and momentum. This is why, in high-energy physics, scientists often talk more about energy and momentum than about speed. Speed quickly becomes a less useful quantity because it stays close to the same value over a wide range of energies. Energy, by contrast, can grow without bound. It becomes the main currency of interactions, determining what kinds of processes are possible and what new particles can be created. This shift in emphasis is reflected in the design of particle accelerators. Engineers focus on achieving higher and higher energies, not higher and higher speeds. The speeds saturate early. The energies keep climbing. The name accelerator is a bit of a misnomer in this sense. After a certain point, the machine is less about making particles go faster and more about making them more energetic. Momentum also plays a central role in shaping the outcomes of collisions. When two high-energy particles meet, their combined momentum and energy determine what can emerge from the interaction. Heavy particles can be created, lighter ones can scatter in new directions, and energy can be redistributed among many different products. All of this is governed by the same conservation laws that hold at lower energies, but the range of possibilities becomes much richer. This richness is part of what makes high-energy physics such a powerful tool for exploring the fundamental structure of matter. By pushing particles into regimes where the cost of acceleration reveals itself so clearly, scientists can probe the deeper layers of the fields and interactions that make up the universe. Yet even here, in these extreme conditions, the same quiet boundary remains in place. The speed of a light continues to mark the edge of what is possible. No matter how much energy is poured into the system, the velocities stay within the same limit. This consistency across scales is one of the most striking features of modern physics. The same rules that govern a ball rolling across a floor also govern particles colliding at energies millions of times greater than anything found in everyday life. The difference lies not in the rules themselves, but in how their consequences unfold. Another way to appreciate the growing cost of acceleration is to think about the flow of energy through fields. When you apply a force to a charged particle, for example, you're interacting with the electromagnetic field. You're not just pushing the particle directly, you're reshaping the field around it. This reshaping propagates outward at the speed of light. The field carries energy and momentum away from the particle in the form of radiation. At high accelerations, this radiation becomes significant. The particle loses energy to the field even as you are trying to give it more. This effect, known as radiation reaction, adds another layer to the cost of acceleration. You're not only fighting against the geometry of space-time, but also against the tendency of the fields to carry energy away. In everyday conditions, this effect is tiny. In extreme conditions, such as in the intense electromagnetic fields near certain astrophysical objects, it can become important. This again shows how energy, momentum, and fields are woven together. You cannot treat them as separate pieces. They form a single, interacting system. Richard Feynman's work in quantum electrodynamics made this interplay especially clear. His diagrams show how particles and fields exchange energy and momentum through the emission and absorption of photons. Acceleration, in this language, is not just a change in velocity, it is a change in how a particle interacts with the field around it. This view brings a certain depth to the idea of cost. It is not just about how much fuel you need or how powerful your engines are. It is about how the entire structure of space-time and fields responds to your attempt to change motion. The closer you push toward the boundary defined by light, the more of the universe you have to involve in the process. More energy flows into the fields, more momentum has to be accounted for, more of the space-time geometry has to bend and adjust. In this sense, the growing cost of acceleration reflects the growing reach of your action. At low speeds, your push affects mostly the object itself. At high speeds, it affects a larger and larger region of the surrounding fields and space-time. This expanding influence is another way of seeing why the universe resists unbounded motion. It is not that it forbids you from trying. It is that trying becomes an increasingly global act, involving more and more of the structure that holds everything together. As this picture settles in, energy and momentum begin to feel less like abstract numbers and more like expressions of how deeply a process is tied into the fabric of reality. The simple act of pushing something to go faster becomes a way of engaging with space-time itself, of redistributing motion between space and time, of reshaping fields and balancing conservation laws. Beyond the rising cost of pushing matter closer and closer to that quiet boundary traced by light, there is another set of changes that unfold just as steadily, but far more gently, changes that do not announce themselves with sparks or collisions, but with clocks that begin to drift and rulers that begin to quietly disagree. These effects sit at the heart of what people often call relativistic mass, time dilation, and length contraction. Three ideas that sound technical, but at their core describe how motion reshapes the very tools we use to describe the world. It can be helpful to start with the one that feels most familiar, time. In daily life, time feels like the most reliable thing you have. Seconds pass, minutes follow, hours stack into days. No matter what you are doing, the clock seems to keep its steady rhythm, indifferent to your motion or your mood. This steady ticking is so deeply embedded in experience that it feels almost like a property of the universe itself, rather than something tied to how you move within it. Relativity gently challenges that assumption. It suggests that time is not a single, universal flow shared by everyone everywhere. Instead, each observer carries their own time with them, shaped by their motion and their position in space-time. To see how this works, imagine two identical clocks. One stays on the ground, the other is placed on a spacecraft that travels at a high, constant speed, and then returns. When the clocks are compared, the one that travelled will show less time has passed. It has ticked more slowly. This is not a mechanical failure. The clock is not broken. Its internal processes have genuinely unfolded more slowly relative to the clock that stayed behind. The atoms inside it have vibrated fewer times. The electrons have completed fewer cycles. Time itself, along that moving path through space-time, has progressed at a different rate. This effect, known as time dilation, becomes noticeable only at very high speeds, but it is always present. Even a person walking across a room experiences it, though the difference is far too small to measure with ordinary clocks. What makes time dilation so striking is not just that clocks run slow, but that this slowing is mutual. From the perspective of the person on the spacecraft, it is the clock on the ground that appears to be running slowly. Each observer sees the other's time as dilated. This might sound like a contradiction, but it is resolved by the fact that the two observers are not in equivalent situations. The traveller must turn around to come back, which involves acceleration. That change of motion breaks the symmetry and leads to a definite difference when the clocks are reunited. The deeper lesson here is that time is not an external backdrop against which motion plays out. It is part of the motion itself. The path you take through space-time determines how much time you experience. This brings us to the idea of proper time, which is the time measured by a clock moving along with an object. Proper time is tied to the object's own world line, the path it traces through space-time. Different paths between the same two events can have different amounts of proper time associated with them. This is a profound shift from classical thinking. In the older view, time between two events was fixed and absolute. In the relativistic view, it depends on the path taken between them. Now, turn attention to length. Just as time stretches and shrinks depending on motion, so does space. An object moving relative to an observer is measured to be shorter along the direction of motion. This is called length contraction. At first glance, this can feel even stranger than time dilation. How can a solid object become shorter just because it is moving? The key lies in how length is measured. To determine the length of an object, you need to record the positions of its two ends at the same time. But in relativity, different observers do not agree on what "at the same time" means. An observer at rest relative to the object uses one set of simultaneous events to mark the ends. An observer moving relative to the object uses a different set of simultaneous events. Because simultaneity itself is relative, the two observers are effectively measuring different pairs of events. the result is a different length. From the perspective of the observer who sees the object moving, the object is contracted. From the perspective of the observer moving with the object has its usual proper length. Just as with time dilation, this effect is mutual. Each observer sees the other's rulers as shortened. What remains unchanged is not the individual measurements, but the space-time interval between events. The combination of space and time measurements stays consistent across frames, even as the pieces shift. Now consider how these two effects, time dilation and length contraction, work together. They are not independent, they are different aspects of the same underlying structure. If time slows down for a moving object and its length along the direction of motion shrinks, then the speed of light can remain the same in all frames. These changes compensate for each other. This compensation is not an added feature. It is the core of the geometry of space-time. The equations that describe how time and space transform between frames ensure that the speed of light remains invariant. Relativistic mass is a term that often enters the conversation at this point, and it is one that has a slightly complicated history. In early treatments of relativity, physicists sometimes described an object's mass as increasing with speed. As an object moved faster, its relativistic mass would grow, making it harder to accelerate. In modern physics, the preferred language is a bit different. Instead of saying that mass increases, physicists usually keep mass as a constant, called the rest mass, and say that the object's energy and momentum increase. Both descriptions point to the same physical behaviour. The faster an object moves, the more energy it carries, and the harder it is to change its motion. Using the concept of relativistic mass can make this feel intuitive. The object seems to become heavier as it moves faster, resisting acceleration more strongly. Using the modern language emphasises that what is really increasing is not the mass itself, but the total energy of the object. Either way, the key idea is that motion changes how an object responds to forces. This change is tied directly to the way time and space are reshaped by motion. To see this connection, imagine pushing on an object that is already moving very fast. From your perspective, its clock is running slowly. This means that, in its own frame, less time passes while you are applying the force. The object has less time to respond to your push, so its change in velocity is smaller. At the same time, its length in the direction of motion is contracted, which affects how momentum is distributed in space-time. These are not separate effects layered on top of each other. They're all part of the same geometric transformation. Another way to see this is to look at how energy and momentum are related in relativity. Instead of being separate quantities, they form components of a single four-dimensional vector in space-time. The magnitude of this vector is related to the rest mass of the object. The components along the time direction and the space directions represent energy and momentum. As the object's motion changes, the way this vector is oriented in space-time changes. The length of the vector stays the same, reflecting the constant rest mass, but its components shift. This picture connects mass, energy, momentum, space and time into a single unified framework. Changes in one aspect are reflected in changes in the others. Now consider how this plays out in practical situations. One of the most famous examples is the behaviour of particles in accelerators. Electrons, for instance, are very light. It does not take much energy to push them to speeds very close to that of light. Once they are in that regime, adding more energy does not make them significantly faster. Instead, it increases their total energy and momentum. From the perspective of the laboratory, the electrons' clocks are running much more slowly than the clocks of the scientists observing them. Their lengths in the direction of the motion are highly contracted. This affects how they interact with the electromagnetic fields. Their trajectories bend differently. Their radiation patterns change. All of these effects can be predicted using the same relativistic framework. Time dilation also shows up in the behaviour of unstable particles. Some particles decay spontaneously after a certain average lifetime. If you create these particles in a laboratory and accelerate them to high speeds, you find that they live longer, as measured in the laboratory frame. From the particle's own perspective, its lifetime has not changed. It still experiences the same amount of proper time before decaying. But because its clock is running slowly relative to the laboratory, it takes longer in laboratory time for that proper time to pass. This effect has been measured in countless experiments and is one of the most direct demonstrations that time dilation is a real, physical phenomenon, not just a theoretical curiosity. Length contraction, while harder to observe directly, also has practical consequences. In high-energy collisions, the contracted shapes of particles affect how their internal structures overlap and interact. In some experiments, particles moving near the speed of light appear flattened along their direction of motion, which influences the distribution of energy and momentum in the collision products. These effects are subtle, but they are part of the same consistent picture. It is also worth noting that gravity adds another layer to this story. In a gravitational field, clocks tick at different rates depending on their position. A clock deeper in a gravitational well, closer to a massive object, runs more slowly than a clock farther away. This gravitational time dilation is a prediction of general relativity, and it has been confirmed by experiments using precise atomic clocks placed at different altitudes. When you combine this with the time dilation due to motion, you get a rich and complex picture of how time flows differently in different circumstances. Systems like GPS have to account for both effects. The satellite's clocks run at a different rate because they are moving fast and because they are farther from the Earth's gravity. Engineers have to correct for both to keep the system accurate. This brings the abstract ideas back into the realm of everyday life. The navigation apps on your phone rely on a deep understanding of how time and space are reshaped by motion and gravity. Relativistic mass, in this broader context, becomes less about a specific term and more about a way of recognizing that energy, not just speed, is what matters most at high velocities. The energy an object carries affects how it curves space-time in general relativity and how it interacts with fields in quantum theory. Motion and energy are deeply linked. Now return to the picture of world lines in space-time. A massive particle's world line always stays inside the light cone. It moves forward in time, with some component of motion through space. As its speed increases, its world line tilts closer to the boundary of the light cone. Time dilation reflects the fact that the projection of this world line onto the time axis becomes shorter. Length contraction reflects the fact that the projection onto the space axis becomes shorter. These projections are how different observers slice space-time into space and time. The world line itself is the same geometric object for everyone. This geometric view can be surprisingly calming. It suggests that beneath all the shifting measurements, there is a single, consistent structure. Observers disagree about the parts, but they agree about the whole. Relativistic effects can feel unsettling because they challenge deeply held intuitions. We are used to thinking of time as universal and space as fixed. Relativity asks us to trade those ideas for something more flexible, but in return it offers a picture of the universe that is more unified. Space and time become aspects of a single entity. Energy and mass become different forms of the same thing. Motion becomes a rotation in a four-dimensional geometry. This unity is part of what makes the theory so compelling. It ties together phenomena that might otherwise seem unrelated, from the ticking of clocks to the bending of light to the creation of particles in high-energy collisions. Another subtle point is that these effects are not just corrections added on top of classical physics. Classical physics is a special case of relativity, one that applies when speeds are much lower than the speed of light and gravitational fields are weak. In that limit, time dilation and length contraction become so small that they can be ignored. Space and time appear separate and absolute. Energy and mass appear distinct. This is why classical physics works so well in everyday life. It is not wrong, it is incomplete. Relativity fills in the missing pieces, revealing what happens when you step outside the comfortable regime of slow motion and gentle gravity. It is also worth reflecting on how these ideas connect, back to the notion of a universal speed limit. Time dilation and length contraction are not just consequences of that limit. They are the mechanisms by which it is enforced. By slowing down time and shrinking lengths for moving objects, space-time ensures that the speed of light remains the same for everyone. It adjusts the measuring sticks and the ticking clocks to preserve that invariance. This is a kind of quiet self-consistency. The universe does not need an external rulebook to keep things in line. The structure of space-time itself takes care of it. Richard Feynman often emphasized that the beauty of physics lies in discovering these kinds of deep connections, where a simple principle leads to a wide range of consequences that all fit together. He liked to remind people that understanding does not mean reducing everything to something trivial. It means seeing how complex patterns arise from simple, well-chosen rules. Einstein's postulate about the speed of light is one such rule. Time dilation, length contraction, and the behaviour of energy and mass all flow from it naturally. It can be helpful to think of motion not as something that happens in space over time, but as something that happens in space-time itself. Objects do not just move through a static world, they trace out paths in a dynamic, four-dimensional structure. The clocks and rulers you use are not neutral bystanders, they are part of that structure. They respond to motion and gravity just as everything else does. This perspective can make the universe feel a little less rigid and a little more interconnected. The act of moving becomes a way of reshaping the very framework in which you exist. Quietly, beneath all the stretching clocks and shrinking rulers, there is a rule that never seems to bend, no matter how fast something moves or how strong a gravitational field becomes. This rule is not written on a sign or enforced by a barrier. It simply emerges from the way space-time is arranged. Causes come before their effects. The universe tells its story in a particular order, and even when different observers disagree about how long things take or how far apart they are, they still agree about which events can influence which others. To ease into this idea, it helps to think about what it means for one event to cause another. In everyday life, the connection feels obvious. You flip a switch, and the light turns on. You drop a glass, and it shatters on the floor. The cause comes first, the effect follows. This sequence feels so natural that it is easy to forget it is also a physical statement, one that depends on how information and influence move through the universe. Every cause must somehow reach its effect. There has to be a chain of events that connects the two. That chain might be a mechanical push, a flow of electricity, a wave of sound, or a beam of light. No matter the form, something has to travel from the cause to the effect. This is where the speed of light quietly steps back into the picture. It is not just a number that tells you how fast light moves. It is the maximum speed at which any influence can travel. If nothing can go faster than light, then nothing can make an effect happen before its cause has had time to arrive. This simple idea becomes surprisingly powerful when you place it into the flexible world of relativity, where time and space depend on how you move. If different observers can disagree about what now means, how can they still agree about cause and effect? The answer lies in the structure of space-time itself. Instead of thinking in terms of a single universal timeline, physics describes a network of possible connections between events. Some events can be linked by signals travelling at or below the speed of light. Others cannot. To visualize this, imagine standing at a particular event, like turning on a flashlight. From that moment, light spreads outward in all directions, forming a growing sphere of influence. Any event that lies inside that sphere at a later time can potentially be affected by what you did. That region is called the future light cone. At the same time, there is a region behind you, a sphere of events whose light has already reached you. Those are events that could have influenced you. That region is called the past light cone. Between these two cones lies a third region, often called the elsewhere. Events in this region are too far away in space, relative to the time difference, for any signal travelling at or below the speed of light to connect them. You cannot affect them yet, and they cannot affect you yet. This structure is not something imposed from the outside. It emerges directly from the geometry of space-time and the universal speed limit. What makes this especially interesting is that different observers, moving relative to one another, slice space-time into space and time in different ways. They may disagree about which distant events are happening at the same time as your flashlight turning on, but they will all agree on which events lie inside your future light cone and which lie inside your past light cone. This agreement is what preserves causality across all reference frames. If an event is inside your future light cone, everyone will agree that it happens after your action and could have been influenced by it. If it is outside, everyone will agree that it could not have been influenced by you yet. So even though simultaneity is relative, causality is not. This distinction is subtle but crucial. It allows the universe to be flexible about time without becoming logically inconsistent. Now consider what would happen if something could travel faster than light. The light cone structure would break down. An event that appears to be in the future of another event in one reference frame could appear to be in its past in another. This would open the door to paradoxes. You could, in principle, send a signal that arrives before it is sent, at least from some observer's point of view. That signal could then prevent its own cause, creating a loop with no consistent solution. This is why the speed of light is often described not just as a speed limit, but as a limit on causality itself. It protects the logical order of events. Richard Feynman enjoyed highlighting this connection. He liked to remind people that the deep rules of physics are not just about numbers and measurements, but about consistency. The universe, as far as we can tell, does not allow contradictions in its own story. Feynman's diagrams make this visible in a simple way. The lines in the diagram represent particles travelling through space-time. The points where they meet represent interactions. The orientation of these lines respects the light cone structure. Energy and information flow forward in time, within the allowed regions, even when diagrams are drawn in ways that look strange, such as particles moving backward in time to represent antiparticles. The overall process still respects causality. These are mathematical tools, not literal pictures of events happening out of order. Another layer of this story appears when you consider how causality works in quantum mechanics. At first glance, the quantum world seems to challenge the very idea of cause and effect. Particles can exist in superpositions, where they are not in a single, definite state. Measurements seem to produce outcomes that are fundamentally random. Entanglement, in particular, has a way of unsettling intuition. Two particles can become linked in such a way that measuring one immediately determines the state of the other, even if they are far apart. This correlation appears to happen instantly, faster than light could travel between them. It is tempting to see this as a violation of causality, but when you look more closely, a different picture emerges. While the correlations appear immediately, they cannot be used to send information faster than light. You cannot control the outcome of your measurement in a way that would allow you to send a message to the distant particle. The universe seems to allow for deep, non-local connections, but it still draws a line at usable, controllable influence. The speed of light remains the limit for communication, even in the quantum realm. This suggests that causality is preserved not just at the level of classical signals, but at the level of information itself. To understand why this matters, think about what it means to send a message. You need to be able to choose what you send. You need to be able to encode information in a way that the receiver can decode. Entanglement does not provide this control. The outcomes are correlated, but they are not directed. So the universe maintains its causal structure, even while allowing for these subtle quantum connections. Another way to see the role of causality is through the conservation laws. Energy and momentum are conserved in every interaction. These conservation laws ensure that the flow of influence through space-time is consistent. In a Feynman diagram, for example, The energy and momentum carried by the lines must balance at each interaction point. This balancing act enforces a kind of local causality. What goes into a vertex must come out. There is no creation or destruction of energy without accounting for it elsewhere. This local consistency, repeated everywhere, builds up into a global order. Now consider the role of time dilation and length contraction in all this. These effects might seem like they would complicate causality, since different observers experience time and space differently, but in fact, they are part of what keeps causality intact. By adjusting how time and space are measured, spacetime ensures that the light cone structure is preserved across frames. If time did not dilate and lengths did not contract, the speed of light would not remain the same in all frames. This would break the consistency of the light cones, and causality could be violated. So these relativistic effects are not just strange consequences of a deeper rule. They are active participants in maintaining the causal order of the universe. It can be helpful to think of space-time as a kind of woven fabric. The threads run in such a way that certain patterns are allowed and others are not. You can stretch the fabric in one direction or another, but the basic weave remains. The light cones are part of that weave. Within this fabric, events are connected by threads of influence. Some threads can reach, others cannot. The pattern of which threads exist and which do not defines the causal structure. This structure also shapes how the universe evolves on large scales. In cosmology, the concept of a horizon plays a central role. Because the universe has a finite age and a finite speed at which information can travel, there are regions that have never been in causal contact with each other. The cosmic microwave background, the faint glow left over from the early universe, shows remarkable uniformity across the sky. Yet, according to simple models, some of these regions should not have had time to exchange information before the light we see was emitted. This puzzle led to the idea of cosmic inflation, a period of rapid expansion in the early universe that allowed regions now far apart to once have been close enough to influence each other. Here again, causality and the speed of light guide the story. The shape of the universe we observe today is deeply tied to which regions could talk to each others in the past. Another place where causality becomes important is in the study of black holes. Near a black hole, the curvature of space-time becomes so extreme that the light cones tip over. At a certain boundary, called the event horizon, the future light cone points inward. Inside that boundary, all possible future paths lead deeper into the black hole. This means that from inside you cannot send a signal back out. The causal structure itself prevents it. The speed of light is still the limit, but the geometry of space-time has reshaped the directions in which light can travel. This shows that causality is not just about speed. It is also about the shape of space-time. Even light moving at its maximum speed can be trapped by a strong enough curvature. In these extreme environments, the familiar notions of past and future become more complex. But the underlying rule remains. There is still a well-defined causal structure. Events inside the horizon can be influenced by events outside in their past, but not the other way around. This one-way relationship is another expression of cause and effect. Now step back from these dramatic examples and return to something simpler, like a conversation between two people. When you speak, sound waves carry your words through the air. They take time to reach the listener. The listener's response then takes time to reach you. This simple exchange is a chain of causal links. Each step respects the speed at which information can travel, whether it is the speed of sound in air or the speed of light in electronic communication. Even when you send a message across the internet, the information does not jump instantly from one device to another. It travels through cables and satellites as electromagnetic signals, constrained by the same universal limit. This means that, in a very real sense, the speed of light shapes the rhythm of modern life. The delays you experience in video calls, the lag in online games, the time it takes for a signal to reach a distant spacecraft, all reflect the causal structure of space-time. These everyday examples can make the abstract idea of causality feel more tangible. The universe is not just a static collection of things. It is a dynamic network of influences, always in the process of connecting one event to another, within the bounds set by its own geometry. Richard Feynman often emphasized that understanding physics means understanding these connections. He liked to say that what you really learn from physics is not just how to calculate numbers, but how to see the relationships between things. Causality is one of the deepest of these relationships. It links the present to the past and the future. It ties local actions to distant consequences. Another subtle aspect of causality appears in the way probabilities work in quantum mechanics. While individual outcomes may be random, the overall structure of cause and effect remains. You cannot use randomness to send a message faster than light. You cannot arrange for a particular outcome to appear at a distant location on demand. This suggests that, even in a universe that allows for uncertainty at the smallest scales, there is a firm boundary around what can be controlled and communicated. This boundary is part of what makes the universe predictable enough to study. Without it, the idea of physical law would lose its meaning. If effects could precede causes, if information could appear without a source, there would be no stable pattern to discover. The fact that the universe does not behave this way is one of the quiet miracles of physics. It allows for both surprise and consistency, for both randomness and order. Another way to frame this is to think about the arrow of time. While the fundamental equations of physics often work just as well backward as forward, the causal structure picks out a direction. The past is the set of events that could have influenced you. The future is the set of events you could influence. This distinction gives time its practical meaning. It is not just a parameter in an equation, it is a map of possible connections. The speed of light defines the boundaries of that map. It tells you how far back you can look and how far forward you can reach. As you look up at the night sky, you are seeing the past. The light from distant stars has travelled for years, centuries or longer to reach you. Those stars, as you see them, may no longer exist in the same form. This is not just a poetic thought. It is a direct consequence of causality and the finite speed at which information travels. In this sense, the universe presents itself to you as a layered history, a stack of past moments arriving in the present through streams of light. Now, imagine what it would mean to break this structure, to send a signal that arrives before it is sent. The neat layering would collapse. The distinction between past and future would blur. This is why so many physicists take the universal speed limit so seriously. It is not just a constraint on motion, it is a foundation for the logical structure of reality. Every theory that has been tested so far, from classical mechanics to quantum field theory to general relativity, respects this structure, even if it expresses it in different ways. Richard Feynman once said that nature has a way of making sure that things do not get out of hand. The more you try to push on one part of the system, the more the rest of the system responds to keep things balanced. Causality is one of those balances. It is maintained by the interplay of space, time, energy, and the speed of light. As this understanding deepens, it becomes clear that the universal speed limit is not just about how fast you can go. It is about how the universe keeps its narrative consistent, how it ensures that stories unfold in a way that makes sense, even across vast distances and extreme conditions, across the vast network of causes, effects, and carefully preserved order. There is another layer of the universe that does not show itself as solid objects or clear-cut signals, but as something quieter and more continuous, a kind of invisible foundation that everything else seems to rise from. This layer is made of fields rather than things, and within it, the question of how information moves takes on a form that is both subtle and surprisingly disciplined. To begin with, it can be useful to step away from the everyday picture of the world as a collection of individual particles, like grains of sand scattered across a surface. That picture works well at human scales, but as physics has looked more deeply, it has found that particles are not the most fundamental pieces of reality. Beneath them lies a set of fields that fill all of space and time, even in regions that appear completely empty. In this view, an electron is not a tiny bead drifting through a void. It is a localized excitation, a small ripple in the electron field. A photon is not a minuscule bullet of light. It is a ripple in the electromagnetic field. Quarks, neutrinos, and all the other members of the particle family are each associated with their own fields, layered together throughout the universe. These fields are always present. Even when there are no particles around, the fields themselves remain, quietly humming with the possibility of excitation. What you call empty space is really a state where all these fields are in their lowest energy configuration, a kind of calm background rather than a true absence. Once you start thinking this way, the idea of information moving from one place to another begins to look different. Instead of imagining a particle carrying a message across a gap, you imagine a field being disturbed in one place, and that disturbance spreading outward. A familiar example of this is a wave on the surface of water. If you drop a pebble into a pond, the water itself does not travel from the centre of the ripple to the edge. What travels is the pattern, the change in the water's shape. Each bit of water mostly stays where it is, but the disturbance passes through. Fields work in a similar way. When something happens in a field, such as an electron changing its energy state, the field is disturbed. That disturbance propagates outward as a wave. In the electromagnetic field, that wave is light. This propagation is how information moves. It is not the field itself that travels, but the change in the field. The speed at which that change spreads is not arbitrary. It is set by the properties of the field and the structure of space-time. For the electromagnetic field, that speed is the speed of light. For the gravitational field, changes also propagate at the speed of light. When a massive object moves, the change in the curvature of space-time it causes does not reach distant regions instantly. It spreads outward at the same universal pace, in the form of gravitational waves. This consistency is not an accident. It reflects a deep connection between the way fields are structured and the geometry of space-time they live in. Quantum field theory brings these ideas together into a single framework. It describes particles as excitations of fields, and interactions as the exchange of these excitations. In this language, forces are not mysterious pushes or pulls across empty space. They are mediated by fields. When two charged particles interact, they do so by exchanging photons, which are excitations of the electromagnetic field. When two masses interact gravitationally, they do so through changes in the gravitational field, which can be described in terms of gravitons in certain theoretical frameworks, though these have not yet been directly observed. Information transfer in this context becomes a question of how these field excitations move and interact. One of the central rules of quantum field theory is something called locality. This rule says that interactions happen at specific points in space-time. A field at one point can influence the field at a nearby point, and that influence can then propagate further. But there is no direct instantaneous action at a distance. This local structure is what ties quantum field theory back to the causal framework defined by the speed of light. It ensures that any influence has to move through space-time step by step, rather than jumping across it. Mathematically, this is expressed through the way field operators behave. Operators associated with events at space-like separated points, meaning points that lie outside each other's light cones, commute. This technical statement has a simple physical meaning. Measurements made at such points cannot influence each other. The order in which they are performed does not matter. There is no causal connection between them. This rule builds the light cone structure directly into the foundation of the theory. It ensures that the speed of light remains the limit for how quickly information can travel. Now, consider how this plays out in a practical situation. Imagine you have a device that emits a burst of light at a particular moment. That burst spreads outward as a wave in the electromagnetic field. At any point in space, the field remains unchanged until the wave arrives. Only then does the field at that point begin to respond. This means that any detector placed somewhere else in the universe cannot register the event until the light has had time to travel to it. No matter how sensitive or sophisticated the detector is, it cannot get the information early. This simple fact is a direct consequence of the local field-based structure of the theory. Quantum mechanics adds a layer of complexity to this picture by introducing uncertainty and probability. When a particle is described by a wave function, that wave function can be spread out over a region of space. This can make it seem as though the particle is, in some sense, present in many places at once. But even here, the underlying fields respect locality. The wave function itself evolves according to equations that propagate information at or below the speed of light. Changes in the wave function at one point influence nearby points, and that influence spreads outward. This is not always obvious because the mathematical description can be subtle. But the principle is built in. One place where this subtlety becomes especially apparent is in the phenomenon of entanglement. When two particles interact, they can become linked in such a way that their properties are correlated even when they later move far apart. If you measure one particle, the state of the other is immediately determined no matter how far away it is. This seems, at first glance, to imply that information has travelled faster than light. However, a closer look shows that no usable information has been transmitted. You cannot choose the outcome of your measurement. You cannot encode a message in it. The correlations only become apparent when the results from both measurements are brought together and compared, and that comparison requires a signal that travels at or below the speed of light. In terms of fields, what is happening is that the two particles share a common quantum state, a single description that spans both of them. Measuring one updates your knowledge of that state, but it does not send a physical signal through the field to the other. The distinction between updating knowledge and transmitting influence is crucial here. The universe allows for correlations that stretch across space, but it does not allow for controllable directed signals to outrun the light limit. This preserves the causal structure while still allowing for the richness of quantum connections. Another way to approach this is to think about how quantum field theory treats the vacuum. Even in its lowest energy state, the vacuum is not completely quiet. Fields undergo constant, tiny fluctuations. Virtual particles appear and disappear, borrowing energy for brief moments allowed by the uncertainty principle. These fluctuations do not carry information in a controllable way. They are random, short-lived and balanced. They do not form a channel through which messages can be sent. Yet, they do play a role in how fields respond to disturbances. They shape the way interactions occur, influencing things like the strength of forces and the behaviour of particles at small scales. This means that even the empty parts of space-time are active participants in the flow of influence, albeit in a way that remains consistent with the speed of light limit. Consider how this looks in a Feynman diagram. The lines representing particles are connected by lines representing virtual particles. These virtual particles can have a wide range of energies and momenta, including values that would not be allowed for real, observable particles. But the overall process, when you look at the diagram as a whole, still respects causality. The initial and final states are connected by a network of interactions that, taken together, do not allow information to appear where it should not be. This network view reinforces the idea that information transfer is not about a single, simple path. It is about a pattern of interactions in fields that collectively obey the same deep rules. Now think about how this plays out in more complex systems, like a piece of technology or a living organism. When you press a button on a remote control, you create a change in the electromagnetic field. That change propagates as a radio wave. The receiver detects the change and responds. Inside the receiver, that signal triggers a cascade of electronic processes, each one involving fields and particles interacting locally. At every step, the influence moves forward through space-time, never jumping ahead of itself. Even inside your own body, when a nerve fires, it sends an electrical signal along a cell. That signal is a change in the electromagnetic field within and around the nerve. It propagates at a finite speed, much slower than the speed of light, but still governed by the same underlying principles. This layered picture, from quantum fields to biological systems, shows how deeply the idea of local, field-based interaction is embedded in the universe. It is also worth noting that different fields can have different characteristic speeds for certain kinds of disturbances. Sound waves, for example, propagate through the air at the speed of sound, which depends on the properties of the medium. But these are not fundamental limits. They are emergent properties of how the medium responds. At a deeper level, the electromagnetic field that underlies those sound waves still respects the speed of light limit. In quantum field theory, the fundamental fields are defined in such a way that their excitations cannot propagate faster than light. This is built into the equations themselves. Another interesting feature of this framework is how it handles the concept of information. In classical physics, information is often treated as something abstract, something you encode in a signal. In quantum field theory, information is tied to the state of the fields. The complete description of a system is given by the configuration of its fields and their quantum states. When something changes, information about that change is encoded in how the field's disturbed. The spread of that disturbance is the spread of information. This makes the speed of information transfer a physical quantity, not just an abstract one. It is limited by the speed at which fields can respond and propagate changes. There is a deep connection here to the idea of entropy and the arrow of time. Information, in a physical sense, is related to the number of possible states a system can be in. As systems evolve, they tend to move towards states with higher entropy, meaning more possible configurations. This evolution is also constrained by causality. The way information about a system state spreads through its environment follows the same light cone structure. When a hot object cools, for example, information about its temperature spreads outward as heat and radiation. The surrounding fields carry that information away, and it cannot travel faster than light. In cosmology, the distribution of information about the early universe is carried to us by the cosmic microwave background. The tiny variations in that radiation encode information about conditions billions of years ago. That information has been travelling through the electromagnetic field ever since, constrained by the same universal limit. This makes the night sky not just a collection of distant lights, but a vast archive of information, a record of past events carried to us by field excitations that have crossed unimaginable distances. Another subtle point is that the speed of information transfer is not always exactly the speed of light in every context. In certain materials, for example, light can appear to travel more slowly, or even faster, due to the way the medium responds to electromagnetic waves. However, these effects do not allow information to be transmitted faster than the speed of light in a vacuum. The underlying signals that carry new, usable information are still limited by the same fundamental bound. This distinction is important because it shows how the universal speed limit can coexist with a wide range of observed behaviours at the surface level. Now, return to the idea of reference frames. Different observers can describe the same field disturbance in different ways. One might see it as a wave spreading out symmetrically. Another might see it as compressed in one direction and stretched in another due to their relative motion. But they will all agree on which events can be influenced by the disturbance and which cannot. The light cone structure remains the same. This invariance is what allows quantum field theory to be compatible with special relativity. The theory is built so that its predictions do not depend on the choice of reference frame. This is not just a philosophical preference, it is a mathematical requirement. If the theory did not respect this symmetry, it would produce different results for different observers, which would undermine its consistency. Richard Feynman was deeply involved in developing the tools that made this framework workable. His diagrams and techniques provided a way to calculate how fields interact and how probabilities for different outcomes can be computed. These tools reveal a universe that is both probabilistic and orderly, uncertain in its details but firm in its boundaries. The speed of information transfer is one of those boundaries. It shapes what can happen, when it can happen, and how different parts of the universe can stay connected. It also shapes how the universe can be known. There are regions of space that are so far away that their light has not yet reached us. We have no information about what is happening there right now. They lie outside our current causal horizon. This horizon is not a limitation of our technology. It is a feature of space-time itself. As the universe expands, this horizon changes. New regions come into view as their light finally arrives. Others move beyond reach as the expansion of space carries them away faster than light can bridge the gap. In this dynamic setting, the flow of information is not just a local concern. It shapes the large-scale structure of the cosmos. Another place where this becomes apparent is in the study of black holes. Near a black hole, the light cones tilt inward. The field disturbances that would normally carry information outward are forced inward instead. This creates a boundary beyond which information cannot escape, at least according to classical general relativity. This raises deep questions about what happens to information that falls into a black hole. Does it disappear? Is it somehow preserved in a subtle way? These questions are still being actively explored and connect quantum field theory, gravity, and the nature of space-time itself. What remains consistent, even in these extreme scenarios, is the role of the speed of light as a guide. It marks the edge of influence, the boundary of connection. The more deeply physicists explore the quantum and gravitational realms, the more they find this same limit appearing sometimes in surprising ways, but always as a central feature. This suggests that the speed of light is not just a property of a particular field, but a reflection of the underlying structure of reality. As this understanding settles in, the picture that emerges is one of a universe woven from fields, with information flowing through them in patterns shaped by geometry and law. Every signal, every interaction, every observation is part of this flow. The calm rule that nothing outruns light is not an external constraint, but an expression of how the fields themselves are built. Gently, after following how information moves through fields and how the universe guards the flow of influence, it becomes natural to look for a way to picture all of this in a form that feels almost like a map. Not a map of countries or oceans, but a map of events, of tiny meetings and exchanges that happen every moment, even in the quietest corners of space. This is where Feynman diagrams step into the story, not as decorations for textbooks, but as a practical and surprisingly intuitive way of tracing how particles interact as they travel through space-time. At first glance, a Feynman diagram can look almost too simple. A few straight lines, a few wavy ones, some points where they meet. There is no detailed drawing of particles, no swirling clouds of fields, no sense of scale or distance. Yet within that simplicity is a remarkable amount of information, carefully compressed into a visual language that physicists use to keep track of some of the most subtle processes in nature. To understand why these diagrams matter, it helps to remember what they are meant to represent. They are not pictures of what actually happens in space, the way a photograph is a picture of a landscape. They are more like accounting sheets. Each line, each point, stands for a mathematical term in an equation that calculates the probability of a certain interaction occurring. But even as bookkeeping tools, they carry a strong physical intuition. They tell a story about who meets whom, what gets exchanged, and how energy and momentum flow from one part of a process to another. Imagine, for example, two electrons approaching each other. In everyday language, you might say they repel each other because they both carry negative charge. In the language of quantum electrodynamics, the interaction is described as an exchange of a photon. In a Feynman diagram, this is drawn as two straight lines representing the electrons, with a wavy line connecting them. The straight lines approach, then bend away from each other. The wavy line connects them at a point where each electron either emits or absorbs the photon. This simple picture encodes a lot. It shows that the force is not an instantaneous push across empty space. It is a mediated interaction. Something is exchanged. Energy and momentum leave one electron, travel along the wavy line and arrive at the other. The wavy line does not represent a real photon that you could detect with an instrument. It represents a virtual photon, a temporary disturbance in the electromagnetic field that exists only as part of the interaction. It cannot be observed directly, but its effects can. This idea of virtual particles is one of the more subtle aspects of the diagrammatic language. Virtual particles do not have to obey the same simple relationships between energy, momentum, and speed that real particles do. They can briefly borrow energy, as long as they pay it back quickly enough to satisfy the uncertainty principle. What keeps this from turning into a loophole for breaking the speed of light limit is that these virtual particles are not carriers of usable information. They are internal parts of the calculation, not messengers you can send signals with. The overall interaction, taken as a whole, still respects causality and the structure of space-time. Now consider how time is represented in these diagrams. Often time is drawn as a vertical or horizontal axis. As you move along the axis, you move from earlier events to later ones. A line slanting upward represents a particle moving forward in time while also moving through space. The point where lines meet is an interaction event, a specific moment in space-time where something happens, like a particle emitting or absorbing another particle. This way of drawing things reinforces the idea of particles as travellers. Each line traces a path through space-time. Each vertex, each meeting point, marks a moment of exchange. What makes this even more powerful is that the same diagram can be interpreted from different reference frames. One observer might see the interaction as happening at one set of times and positions. Another observer, moving relative to the first, will assign different times and positions. But the structure of the diagram, the way the lines connect, remains the same. This reflects a deeper truth. The underlying process does not depend on who is watching. The energy and momentum still flow in the same way. The conservation laws still apply at each interaction point. This invariance is one of the reasons Feynman diagrams became so widely used. They provide a way to keep track of interactions that respects the symmetries of space-time. Another striking feature of these diagrams is how they blur the line between what you might call before and after. In some cases, a diagram can be drawn in more than one way that represents the same physical process. You can flip it, rotate it, or reinterpret which line is incoming and which is outgoing. This flexibility reflects the underlying symmetry of the equations. The same interaction can often be viewed as a particle being absorbed or as an antiparticle being emitted, depending on how you choose to label the lines. For example, a line representing an electron moving backward in time can be reinterpreted as a positron, the electron's antiparticle, moving forward in time. This is not a statement about actual time travel. It is a mathematical equivalence that makes the calculation simpler and more elegant. This reinterpretation highlights the idea that particles and antiparticles are deeply related, two aspects of the same underlying fields. Now, think about how these diagrams are used in practice. When physicists want to calculate the probability of a certain process, such as an electron scattering off another electron or a particle decaying into two others, they draw all the possible diagrams that represent that process at a given level of approximation. Each diagram corresponds to a mathematical expression. The more complicated the diagram, the more complex the expression. The final probability is found by adding up the contributions from all the relevant diagrams. This is where the idea of particles taking all possible paths comes back into view. Each diagram represents a class of possible ways the interaction could unfold. The sum of all these possibilities gives you the final, observed outcome. Some diagrams represent simple, direct interactions. Others represent more complicated sequences of exchanges, with multiple virtual particles appearing and disappearing along the way. Even when the final result looks simple, the internal story can be rich and layered. For instance, consider the interaction between two photons. In classical physics, light beams pass through each other without interacting. In quantum electrodynamics, two photons can interact indirectly by temporarily creating a pair of charged particles, such as an electron and a positron, which then annihilate back into photons. In a Feynman diagram, this is drawn as two wavy lines entering, connecting to a loop of straight lines, and then two wavy lines leaving. The loop represents the temporary appearance of the electron-positron pair. This process is rare, but it is allowed. The diagram captures the idea that even interactions that seem impossible at first glance can occur through more complex internal pathways. This is another place where the cost of energy becomes important. Creating a heavy particle pair requires a lot of energy. The higher the mass of the particles in the loop, the less likely the process is to occur. This is reflected in the mathematical weight of the diagram. Energy and momentum conservation still apply at each vertex. The fields and particles must balance their accounts at every step. Now think about how these diagrams relate to the speed of light and the flow of information. The lines in the diagram represent particles and field excitations moving through space-time. The way they are connected reflects which events can influence which others. Even though the diagrams are drawn on a flat page, they encode the light cone structure implicitly. The allowed connections are those that respect causality. You cannot draw a diagram where a particle influences another particle outside its future light cone. The mathematical rules that define which diagrams are allowed prevent that. This is another example of how the speed limit is built into the foundations of the theory, not added as an afterthought. There is also an interesting connection between Feynman diagrams and the idea of symmetry. The laws of physics have certain symmetries, such as the symmetry between matter and antimatter, or the symmetry under rotations in space. These symmetries show up in the way diagrams can be transformed without changing their meaning. You can often swap lines, flip orientations, or reinterpret directions, and still represent the same physical process. This reflects the fact that the underlying fields and interactions are governed by mathematical structures that are invariant under certain transformations. Another layer of meaning appears when you consider how diagrams change as you include more and more details. At the simplest level, you might draw only the most basic diagram for a process, with a single exchange of a virtual particle. At higher levels of precision, you include diagrams with loops, multiple exchanges, and more complicated structures. These represent subtle effects, like small corrections to the strength of a force or tiny shifts in a particle's properties. These corrections can be measured experimentally, and the agreement between the calculations and the measurements is often astonishingly precise. In some cases, the predictions match observations to many decimal places. This precision is one of the great successes of quantum field theory and the diagrammatic approach. It also reinforces the idea that these diagrams are not just convenient pictures. They are deeply connected to how nature actually behaves. Yet, it is important to keep in mind their limitations. A Feynman diagram is not a literal snapshot of what happens in space and time. It does not show a particle flying along a wavy line or a virtual particle popping in and out of existence like a tiny creature. It is a symbolic representation of a mathematical term, a way of organizing a complex calculation. Still, as with many good symbols, it captures something essential about the process. It shows that interactions are local. They happen at points. They involve exchanges. They respect conservation laws. They unfold within the boundaries set by space-time. This symbolic power is part of what made Feynman such an influential figure. He did not just provide new equations, he provided new ways of thinking and new ways of seeing. He often emphasized that physics is not about finding the true picture of reality, but about finding models that work, that allow you to predict what will happen in experiments. Feynman diagrams are one such model. They do not tell you what is really happening in some ultimate sense. They tell you how to calculate the probabilities of different outcomes. The fact that this method works so well suggests that it is capturing something deep about the structure of interactions. Another interesting aspect of these diagrams is how they highlight the role of scale. At very small distances and very short times, the number of possible diagrams grows rapidly. The interactions become more complex. Virtual particles of higher and higher energies can appear in loops. This is where some of the challenges of quantum field theory arise. The calculations can produce infinities that have to be carefully handled through a process called renormalization. Renormalization is a way of redefining certain quantities so that the final, observable predictions remain finite and meaningful. It is another example of how the theory maintains consistency, even when the internal bookkeeping becomes complicated. This process can feel abstract, but it has a physical interpretation. It reflects the fact that what you observe at one scale depends on what is happening at smaller scales. The effective strength of a force, for example, can change depending on how closely you look. In the diagrammatic language, this shows up as contributions from loops and higher-order diagrams. Once again, the speed of light and the structure of space-time remain in the background, guiding what kinds of diagrams are allowed and how their contributions are combined. Another place where diagrams reveal something subtle is in the way they treat time. Although time is drawn as an axis, the mathematical expressions associated with the diagrams often involve integrating over all possible times at which interactions could occur. This reflects the quantum idea that events do not happen at sharply defined moments unless they are measured. The probability amplitudes account for all possible interaction times. Despite this, the final results still respect causality. The integrals are set up in such a way that effects do not appear before causes. This careful balance between flexibility and constraint is a recurring theme in physics. The universe allows for a wide range of possibilities, but it keeps them within a structured framework. Now, consider how these ideas connect back to the everyday world. The forces that hold atoms together, that allow chemistry to happen, that give materials their strength, are all described by interactions that can be represented by Feynman diagrams. Every chemical bond, every electrical current, every beam of light interacting with matter can, in principle, be traced back to exchanges of particles and fields encoded in these simple drawings. This does not mean that you need to draw a diagram to understand why a magnet sticks to a refrigerator. But it does mean that there is a deep, unified description that connects these everyday phenomena to the same fundamental processes that occur in the heart of stars and the collisions of particles in accelerators. This unity is one of the quiet beauties of physics. A single framework can describe a vast range of scales and situations. Feynman himself often delighted in pointing out these connections. He enjoyed showing how a simple idea, like the exchange of a photon, could explain both the repulsion of two electrons and the attraction of a magnet to a piece of metal. Another subtle point worth noting is that the diagrammatic approach is not limited to electromagnetic interactions. Similar diagrams can be drawn for the strong force, which holds atomic nuclei together, and the weak force, which governs certain types of radioactive decay. Each of these forces has its own kinds of lines and vertices, representing different fields and particles. But the underlying structure, local interactions, conservation laws, and respect for causality remains the same. This suggests that there is a common pattern underlying all the fundamental interactions, a pattern that might one day be unified into a single, even deeper framework. As you sit with the image of these diagrams as maps, it can be helpful to imagine the universe as a vast, constantly evolving network of such interactions. Every moment, countless lines are being drawn and erased, countless vertices are forming and dissolving as particles and fields interact. Most of these processes are too small, too fast, or too subtle to ever be directly observed, but together they build up the stable, familiar world you experience. The table you rest your hand on feels solid because of a balance of electromagnetic interactions between the atoms in your hand and the atoms in the table. Those interactions can be traced at a fundamental level to the exchange of photons represented in diagrams. The warmth you feel from a cup of tea is energy flowing through fields, photons being absorbed by molecules, a story that could also be drawn in the same symbolic language. This universality gives the diagrams a certain quiet power. They are not just tools for specialists. They are glimpses into a way of seeing the world that connects the very small to the very large, the abstract to the tangible. Woven into every exchange of energy, every flicker of motion, and every quiet moment where nothing seems to happen at all, there is a single steady number that keeps showing up, not as a background detail, but as a kind of organising principle for how the universe holds itself together. The speed of light is often introduced as a limit, a fastest possible pace for anything that moves or communicates. Yet when you step back and look at the broader picture, it becomes clear that this number does far more than cap velocities. It helps shape the very structure of reality, guiding how space, time, matter, and information fit together into a coherent whole. To begin exploring this role, it can be helpful to think about how deeply the speed of light is embedded in the equations that describe the world. It appears in the laws of electromagnetism, in the geometry of space-time, in the relationship between mass and energy, and in the way fields evolve and interact. This is not a coincidence. It suggests that light speed is not just a property of a particular phenomenon, but a fundamental conversion factor that links different aspects of reality. In a very practical sense, the speed of light tells you how to translate between distance and duration. If you know how long something takes to happen, you can multiply by the speed of light and get a distance. If you know a distance, you can divide by the speed of light and get a time. This simple relationship becomes the backbone of modern measurements. The meter itself is defined in terms of how far light travels in a fraction of a second. Space is, in a way, measured by time. This choice reflects a deeper truth. Space and time are not independent quantities that just happen to be related by speed. They are parts of a single structure, space-time, and the speed of light is the number that sets the scale of that structure. Imagine space-time as a vast grid, not of squares, but of relationships. Each event is a point in this grid, and the separation between events can be described in terms of both space and time. The speed of light defines the slope of the lines that connect these points in a causal way. It determines which events can be linked by a signal or an influence. In this picture, light cones become one of the most important geometric features. From any event, you can draw a cone that represents all the possible future events that can be influenced by it, and another cone that represents all the past events that could have influenced it. The sides of these cones are traced by light itself. They are not arbitrary. They are fixed by the speed of light. Everything that happens in the universe unfolds within this network of cones. Massive objects move inside them. Light moves along their surfaces. Events outside them remain causally disconnected, at least for a time. This geometric structure does not depend on the particular details of the situation. It is the same whether you are looking at the motion of a planet, the decay of a particle, or the evolution of a galaxy. The speed of light sets the same boundaries everywhere. Now consider how this structure shapes the idea of simultaneity. In a classical view, you might imagine a series of horizontal slices through space-time, each one representing a moment in time that stretches across the entire universe. Every observer shares these slices, and they all agree on which events are happening now. Relativity replaces this picture with something more flexible. Different observers draw different slices. What one observer calls now may include events that another observer considers part of the past or the future. The tilt of these slices depends on the observer's motion. Despite this, the light cones remain fixed. No matter how you tilt your slice, the cones stay the same. They define a structure that all observers share. This shared structure is what gives reality its coherence. Even though people moving in different ways may disagree about when things happen, they still agree about what can influence what. They still agree about the causal order of events. The speed of light is the key to this agreement. It anchors the geometry of space-time in a way that does not depend on perspective. Another place where this anchoring shows up is in the relationship between mass and energy. Einstein's equation, E equals mc squared, tells you that mass is a form of energy, and the speed of light squared is the factor that converts between the two. This means that the same number that limits how fast things can move also determines how much energy is stored in a given amount of matter. A small mass corresponds to an enormous amount of energy because the speed of light is so large. This connection has profound consequences. It explains how stars can shine for billions of years, converting a small fraction of their mass into light and heat. It explains how nuclear reactions can release such large amounts of energy. It shows that matter and energy are not separate categories, but different expressions of the same underlying quantity. In this sense, the speed of light does not just shape motion and communication, it shapes the very substance of the universe. Now, think about how this plays out at the level of fields. Every fundamental field in physics, from the electromagnetic field to the gravitational field, evolves according to equations that respect the speed of light as the maximum speed of propagation. If something changes in a field at one point, that change spreads outward, not instantly, but at a finite speed. This means that the influence of any event is always delayed. There is always a region of space-time that has not yet been reached by that influence. This delay creates a natural sense of separation and independence between different parts of the universe. What happens in one galaxy does not immediately affect another. The effects take time to travel. This is part of what allows complex structures to form. Regions of the universe can evolve somewhat independently, at least for a while, before their histories become intertwined through the exchange of light and other signals. In cosmology, this idea becomes especially important. The universe has a finite age. There has only been a certain amount of time for light to travel since the beginning of cosmic expansion. This means that there is a limit to how far we can see and how far we can be influenced by distant events. This limit defines the observable universe, a sphere centred on the observer, with a radius set by the speed of a light and the age of the cosmos. Beyond this sphere, there are regions of space that exist but whose light has not yet reached us. They are part of the universe, but not yet part of our observable reality. This introduces a subtle distinction between what exists and what can be known. The speed of light is what separates these two categories. Another layer of this story appears when you consider how the universe has changed over time. In the early moments after the Big Bang, everything was much closer together. Regions that are now billions of light years apart were once near enough to exchange information. As the universe expanded, those regions were carried apart. Some of them moved beyond each other's horizons, meaning that no signal sent today from one will ever reach the other, because the space between them is expanding too quickly. Here, the speed of light interacts with the expansion of space in a subtle way. While nothing can move through space faster than light, space itself can expand in such a way that the distance between 2 points grows faster than light can bridge. This does not violate the speed limit because the limit applies to motion through space, not to the expansion of space itself. Still, the result is that parts of the universe become permanently causally disconnected. This shapes the large-scale structure of reality. It determines which regions can ever influence each other and which will remain forever separate. Now, bring this back down to smaller scales. At the level of atoms and particles, the same principles apply. When an electron in an atom changes its energy state, the electromagnetic field around it is disturbed. That disturbance spreads outward at the speed of light. This means that even within a tiny system, there is a finite time for different parts to learn about changes. This finite speed can have measurable effects. In some high-precision experiments, the delay in field propagation has to be taken into account to accurately predict the behaviour of particles. Another interesting consequence of the speed of light is how it shapes the concept of rigidity. In everyday language, you might think of a rigid object as one where all parts move together. If you push one end of a rod, the other end moves immediately. In reality, no object is perfectly rigid. The push is transmitted through the object as a wave of atomic interactions, which travels at a finite speed, much slower than the speed of light. This means that even at the scale of solid objects, the finite speed of information transfer shapes how things respond. If you could somehow push one end of a very long rod extremely quickly, the other end would not respond instantly. There would be a delay, determined by the speed at which mechanical disturbances travel through the material. At a deeper level, this mechanical speed is itself built on electromagnetic interactions, which are constrained by the speed of light. This shows how the universal speed limit filters down into the behaviour of everyday materials. Another place where the speed of light shapes reality is in the way energy is distributed and stored. Fields can carry energy, and they can also store it. The electromagnetic field, for example, stores energy in the form of electric and magnetic fields. This energy can move, but it cannot move faster than the field disturbances themselves. This means that when you charge a capacitor, the energy does not instantly fill the space between the plates. It flows in, guided by the electromagnetic field at a finite speed. These kinds of details are often invisible in everyday use, but they are part of the same underlying structure. Now consider how the speed of light shapes the idea of measurement. Whenever you measure something, you are in one way or another using light or some other field to gather information. Your eyes use photons, cameras use photons, radar uses radio waves, which are a form of light. Even particle detectors often rely on light produced when particles interact with certain materials. This means that there is always a delay between an event and your knowledge of it. You never observe things as they are right now. You observe them as they were when the light left them. For nearby objects, this delay is so small that it does not matter. For distant objects, it becomes significant. When you look at the moon, you see it as it was a little over a second ago. When you look at the sun, you see it as it was about 8 minutes ago. When you look at a distant galaxy, you see it as it was millions or billions of years ago. This turns the universe into a kind of time machine. Distance becomes a measure of how far back in time you're looking. This temporal layering is another way the speed of light shapes the structure of reality. It means that the present you experience is a collage of past moments from different distances. There is no single, global present that you can observe. There is only your local present, surrounded by a shell of past light from farther and farther away. This has philosophical implications as well as physical ones. It suggests that now is not a universal feature of the universe, but a local feature of each observer. Another subtle role of the speed of light appears in the way physical laws are formulated. Modern theories are built to be Lorentz invariant, meaning they look the same in all inertial reference frames. This invariance is tied directly to the constancy of the speed of light. It ensures that the equations do not single out a preferred frame of reference. This symmetry is one of the guiding principles in constructing new theories. When physicists propose new particles or new interactions, they check whether the equations respect this invariance. If they do not, the theory is usually considered suspect. This shows how the speed of light acts as a kind of gatekeeper, shaping not just what happens in the universe, but what kinds of theories we consider acceptable descriptions of it. Another way to see this gatekeeping role is through the concept of horizons. In addition to the cosmological horizon mentioned earlier, there are horizons associated with black holes. At the event horizon of a black hole, the escape speed equals the speed of light. Inside that boundary, even light cannot escape. The structure of space-time is such that all future-directed paths lead inward. This creates a region of the universe that is permanently hidden from the outside. Information can go in, but it cannot come out. This one-way nature is another expression of how the speed of light shapes reality. It defines not just limits on motion, but limits on knowledge. The study of what happens to information that falls into a black hole has become one of the central problems in theoretical physics. It touches on deep questions about quantum mechanics, gravity, and the nature of space-time. Even here, in one of the most extreme environments imaginable, the speed of light remains a central character. Now, consider how this speed limit influences the stability of matter. Atoms are held together by electromagnetic interactions. The electrons in an atom move in ways that are described by quantum mechanics, but the fields that mediate their interactions propagate at the speed of light. This finite propagation speed helps prevent runaway instabilities. It ensures that changes in one part of the atom do not instantaneously affect all other parts. This contributes to the overall stability of atomic and molecular structures. Another subtle effect of the speed of light is in the way radiation is emitted. When a charged particle accelerates, it emits electromagnetic radiation. This radiation carries energy and momentum away from the particle. The emission and propagation of this radiation are governed by the same light speed limit. The pattern of radiation depends on how the particle's motion changes over time, and the effects of that change spread outward at a finite pace. This means that the fields around an accelerating charge are not simply updated everywhere at once. There is a kind of memory in the field, a record of what the particle was doing a moment ago, carried outward by the radiation. This memory effect can influence the motion of the particle itself through a phenomenon known as radiation reaction. The particle feels a kind of self-interaction because it is interacting with the field it created earlier. This is another example of how the speed of light shapes the dynamics of systems in subtle ways. All of these threads point to the same conclusion. The speed of light is not just a limit on how fast things can go. It is a structural constant that appears in the deepest descriptions of space, time, matter, and interaction. It defines the geometry of space-time. It sets the scale for converting mass into energy. It governs how fields evolve and how information spreads. It shapes the horizons of knowledge and the stability of structures. In this sense, the speed of light is less like a speed and more like a rule about how reality is put together. Richard Feynman often spoke about the importance of looking for the simple ideas that sit behind complex phenomena. He liked to say that if you really understand something, you can explain it in simple terms. The speed of light is one of those simple ideas. It is just a number, a rate. Yet from it flows a remarkable amount of structure. Imagine for a moment setting aside everything that has felt stable and dependable about the universe so far, and allowing a single, quiet assumption to slip. Not a dramatic explosion or a sudden collapse, just the gentle idea that something, somewhere, might be able to move faster than light. At first, this might sound like a small change, a technical detail that only physicists would worry about. But when you follow this idea carefully, it begins to tug at nearly every thread that holds the structure of physical law together. To begin exploring what this would mean, it helps to return to the role that the speed of light plays as more than a limit. It is a boundary that defines how space and time are connected, how causes lead to effects, and how energy and information move through fields. Removing or bypassing that boundary does not just add a new possibility. It reshapes the entire framework in which all other possibilities are defined. One of the first places this reshaping becomes visible is in the geometry of space-time itself. In the familiar picture, space-time is organised around light cones. These cones separate what can be influenced from what cannot, what lies in the past from what lies in the future. They give every event a clear set of possible connections. If something could move faster than light, it would not be confined to moving inside or along these cones. It could cross from one region to another that, in the standard picture, is considered causally disconnected. This would mean that events which, in one reference frame, lie outside each other's influence could suddenly become linked. The clean separation between can affect and cannot affect would blur. Now, consider how this looks from the perspective of different observers. In relativity, different observers disagree about which distant events happen at the same time. This disagreement is already built into the theory, but it's carefully managed by the light cone structure. Even though people may slice space-time differently into now surfaces, they still agree on the causal order of events. If faster-than-light motion were possible, this agreement could break down. An event that appears to be an effect following a cause in one frame could appear to be the cause following the effect in another. The sequence of events would no longer be consistent across perspectives. This is not just a philosophical discomfort. It creates the possibility of real contradictions. To see how, imagine a device that can send a signal faster than light. From your perspective, you send the signal, and it arrives at a distant location almost immediately. But from the perspective of someone moving relative to you, that same signal might arrive before you sent it. If the person at the receiving end then sends a reply back using the same faster-than-light method, that reply could arrive before your original message was sent. This creates a loop where information appears to come from the future and influence the past. In such a loop, you could receive a warning telling you not to send a message, and as a result you never send it. But if you never send it, you never receive the warning. The story has no consistent resolution. This kind of scenario is often called a causality paradox, and it is one of the main reasons physicists are cautious about the idea of faster-than-light signals. The issue is not just that such signals would be surprising, it is that they would undermine the logical consistency of physical law. Now think about how this would affect the conservation laws. Energy and momentum are conserved in every interaction. This is tied to the symmetries of space-time. Conservation of energy is connected to the symmetry of time. Conservation of momentum is connected to the symmetry of space. If faster-than-light motion were allowed, the neat structure of these symmetries could be disrupted. For example, if a particle could appear at a location before the cause of its appearance, it would be difficult to define a consistent account of where its energy came from. You might try to track energy flowing from the past into the future, but if the particle's arrival precedes its creation in some frames, the flow of energy would appear to go backward in time. This does not fit comfortably with the idea of conservation as a local, step-by-step accounting. In the standard picture, energy and momentum flow along world lines and through interaction points in a way that respects the light cone structure. Each exchange can be traced from one event to another in a forward-in-time sequence. Faster-than-light motion would allow world lines that cut across this structure in unusual ways, making it harder to define a clear, consistent flow. Another place where the impact would be felt is in the behaviour of fields. Fields evolve according to equations that propagate changes at finite speeds. This is what keeps interactions local. If something could move faster than light, it would mean either that there is a new kind of field that propagates faster, or that existing fields can somehow transmit influences beyond their usual limits. In either case, the idea of locality would be challenged. Interactions could become non-local in a direct, controllable way, not just in the subtle, correlation-based way seen in quantum entanglement. This would mean that what happens in one place could directly and immediately affect what happens somewhere else, without a chain of intermediate steps. Such a universe would behave very differently from the one we observe. It would be harder to define independent systems, because everything could, in principle, influence everything else without delay. This would make it difficult to isolate experiments, to define boundaries between cause and effect, or even to talk meaningfully about what happens here as opposed to there. Now, consider the role of the speed of light in defining mass and energy. The relationship between energy, momentum, and mass is built around the idea that the speed of light is the same in all frames and is the maximum speed for massive particles. If something could exceed this speed, the familiar relationship would have to be revised. In the standard equations, as an object's speed approaches the speed of light, its energy grows without bound. This is what prevents massive objects from ever reaching that speed. If faster-than-light motion were possible, this barrier would either have to be removed or bypassed. That would require a new relationship between energy and speed. One theoretical idea that sometimes appears in discussions is the concept of tachyons, hypothetical particles that always move faster than light. In some mathematical models, tachyons have imaginary mass, a strange property that leads to unusual behaviour. In these models, the energy of a tachyon decreases as its speed increases. Slowing down a tachyon would require adding energy, while speeding it up would release energy. This inversion of the usual relationship between energy and speed highlights how deeply the speed of light is woven into the structure of physical law. Changing it flips some of the most basic intuitions upside down. Even if tachyons remain purely speculative, they serve as a useful illustration of how allowing faster-than-light motion would require rethinking the foundations of energy and momentum. Another area that would be affected is the concept of time itself. In the standard relativistic picture, time dilation and length contraction work together to preserve the speed of light across frames. If faster-than-light motion were allowed, this delicate balance could be disrupted. Observers might find that the transformation rules between frames no longer preserve the same structure. The symmetry that makes the laws of physics look the same to everyone could break. This would mean that some frames of reference might become preferred, singled out by the presence of faster-than-light effects. The idea that there is no absolute rest frame, no special perspective from which the universe looks truly at rest, is a cornerstone of modern physics. Faster-than-light motion could undermine this principle. Now think about how this would influence the arrow of time. While the fundamental equations often work both forward and backward in time, the causal structure imposed by the speed of light gives time a practical direction. You can influence the future, but not the past. If signals could travel faster than light, and therefore in some frames backward in time, this distinction could become blurred. It might become possible, at least in principle, to send information into what some observers would call the past. This raises questions about free will, predictability, and the consistency of physical law. If the future can influence the past, how do you define a cause? How do you define an effect? The neat one-way chain that underlies so much of scientific reasoning could become tangled. Another layer of this story appears in thermodynamics. The second law of thermodynamics states that, in an isolated system, entropy tends to increase over time. This gives time its familiar arrow at the macroscopic level. If faster-than-light influences allowed information or energy to move backward in time, this could, in principle, allow for processes that decrease entropy in ways that are not accounted for in standard thermodynamics. This would challenge one of the most robust and well-tested principles in physics. Now, consider how the structure of space-time itself might respond. In general relativity, mass and energy tell space-time how to curve, and space-time tells mass and energy how to move. If faster-than-light motion were possible, the paths that mass and energy take through space-time would include trajectories that lie outside the usual light cones. This could lead to unusual curvature patterns, perhaps even allowing for exotic structures like closed time-like curves, paths through space-time that loop back on themselves in time. Some solutions to Einstein's equations already allow for such curves under extreme and highly idealized conditions, such as in certain rotating universes or hypothetical structures like wormholes. These solutions are often considered unphysical, in part because they threaten causality. Allowing faster-than-light motion could make such exotic structures more than mathematical curiosities. It could bring them into the realm of physical possibility. This possibility has inspired many speculative ideas in science fiction, such as time machines and faster-than-light travel through hyperspace. In these stories, the universe often has to invent new rules to avoid paradoxes, like self-consistency conditions that prevent actions in the past from changing the present. In physics, however, there is no evidence for such built-in safeguards beyond the speed of light itself. Another consequence of faster-than-light motion would be its impact on the concept of a horizon. Horizons, whether in cosmology or around black holes, are defined by the speed of light and the structure of space-time. They mark boundaries beyond which information cannot reach an observer. If something could move faster than light, It could cross these boundaries in ways that are currently forbidden. Information could escape from inside a black hole's event horizon. Signals could reach regions of the universe that are currently beyond the cosmological horizon. This would dramatically change the way the universe is connected. The idea of hidden regions, of parts of reality that are fundamentally inaccessible, would no longer hold in the same way. Knowledge and influence could spread more widely, potentially making the universe more tightly linked than it is now. Now think about how this would affect the process of measurement. In the standard picture, any measurement involves an exchange of information between the system and the observer, mediated by fields that propagate at or below the speed of light. This creates a natural separation between what is measured and when the result is known. If information could travel faster than light, this separation could shrink or vanish. Observers might be able to access information about distant systems in ways that bypass the usual delays. This could lead to a very different kind of observational science, one where distance no longer implies delay. But it would also make it harder to define what it means to make a measurement at a particular time, since the ordering of events could vary between frames. Another subtle effect would be on the structure of quantum theory itself. Quantum field theory is built to respect relativistic causality. Operators associated with space-like separated regions commute, ensuring that measurements in those regions cannot influence each other. If faster-than-light influences were allowed, this mathematical structure would have to be revised. The clean separation between independent measurements could break down. The probabilistic framework that relies on this separation might need to be rethought. This could have far-reaching implications for how probabilities are assigned and how outcomes are predicted. It might even challenge the very notion of a well-defined quantum state evolving over time. Another angle to consider is the role of the speed of light in defining the maximum rate at which information can be processed. In physics, there are limits on how quickly a system can change its state, often related to the energy it has and the size of the region it occupies. These limits are tied in part to the speed at which signals can propagate within the system. If faster-than-light motion were possible, these limits might be relaxed. This could, in principle, allow for much more rapid computation or more tightly packed information storage. Such possibilities are highly speculative, but they illustrate how deeply the speed of light is woven into the practical as well as the theoretical limits of the universe. Another point of impact would be on the idea of isolation. In the current framework, it is possible to talk about systems that are effectively isolated from each other for a time, because signals take time to travel. This allows for the idea of local experiments, where you can study a system without worrying about distant influences. If faster-than-light signals were available, true isolation might be impossible. Distant events could always, in principle, influence local systems almost immediately. This would change the way scientific experiments are designed and interpreted. It would also change the way complex structures, like ecosystems or societies, might evolve, since the flow of information and influence would be much more rapid and far-reaching. As these consequences accumulate, a pattern begins to emerge. Allowing faster-than-light motion is not like adding a new feature to an otherwise unchanged universe. It is like altering the underlying grammar of reality, the way events are ordered, the way energy is conserved, the way fields interact, the way time is defined, the way information is transmitted. All of these are tied, directly or indirectly, to the speed of light. Changing that one element sends ripples through the entire structure. This is one of the reasons physicists often say that the speed of light is not just a property of light, it is a property of space-time itself. It defines how the universe is stitched together, how different parts relate to each other, and how the story of events can unfold without contradiction. Richard Feynman liked to emphasize that the strength of a physical theory lies in how many things it can explain with a small number of principles. The constancy of the speed of light is one such principle. From it flows a wide range of consequences, from time dilation and energy mass equivalence to causality, and the structure of quantum field theory. Speculating about faster-than-light motion is, in a way, a test of how tightly these consequences are bound together. So far, every careful examination suggests that they form a coherent whole. Pulling on one thread threatens to unravel many others. This does not mean that the universe could not, in principle, be different. It means that the universe we observe is deeply shaped by this one, steady limit. It naturally leads toward a more grounded question. If faster-than-light motion seems to destabilize so much of physical law, what does the actual limit mean for our ambitions, our technologies, and our dreams of reaching the stars? How does this boundary shape not just abstract theory, but the practical possibilities of exploration and connection across the vast distances of space? Practical dreams often begin far from equations and diagrams, in the simple human desire to reach farther, to see more, to connect across distances that once felt unreachable. From the first boats crossing rivers to the first signals sent through wires, technology has always been about extending the reach of action and knowledge. When you place those dreams into a universe shaped by relativity, however, they encounter a quiet but firm framework that guides what is possible, what is difficult, and what remains, at least for now, out of reach. To understand how this framework influences technology, it helps to return to the idea that motion, energy, and information are not independent ingredients. They are woven together by the geometry of space-time and by the speed of light. Any device that moves, communicates, measures, or computes is, in one way or another, working within this structure. Start with the most familiar technological ambition: travel. For most of human history, the main limit on how far you could go was endurance. How long could you walk, sail, or ride before you needed to rest or resupply? As engines grew more powerful, speed became the focus. Faster vehicles meant shorter journeys, and for a while, it seemed as though there might be no practical ceiling. Relativity introduces a different kind of ceiling, one that does not depend on engineering skill or material strength. It is not about how powerful your engines are or how streamlined your vehicle is. It is about the relationship between energy and velocity itself. As a spacecraft accelerates and approaches the speed of light, the energy required to increase its speed grows without bound. Each additional fraction of a percent of light speed demands more energy than the last. This means that no matter how advanced your technology becomes, there is a point where adding more fuel or more power produces diminishing returns in terms of speed. This has a direct impact on how interstellar travel is imagined. The stars are separated by distances measured in light years. Even at a significant fraction of the speed of light, a journey to the nearest star would take years from the perspective of someone on Earth. From the perspective of travellers on board a fast-moving spacecraft, time dilation would make the journey feel shorter. Their clocks would tick more slowly, and they would experience less time during the trip. But this does not change the fact that, for the rest of the universe, the journey still takes years or decades. This creates a kind of split reality. The travellers and those who stay behind live through different amounts of time between the same departure and arrival events. Technology has to operate within this split, managing communication, navigation, and coordination across frames that do not share a single universal clock. Now consider communication. In a relativistic universe, sending information is fundamentally tied to the propagation of fields. Whether you use radio waves, laser beams, or any other form of electromagnetic signal, the message travels at the speed of light. This imposes a delay that cannot be engineered away. You can make your transmitter more powerful, your receiver more sensitive, your signal more efficient, but you cannot make the message arrive sooner than the light travel time allows. This becomes especially important in space exploration. A command sent to a spacecraft near Mars takes several minutes to arrive. A signal sent to a probe at the edge of the solar system can take hours. For distant stars, the delay would be measured in years. This means that real-time control becomes impossible beyond a certain distance. Any technology that operates far from Earth has to be designed to make decisions on its own, because by the time a message reaches it and a response comes back, the situation may have changed completely. This requirement for autonomy is not just a matter of convenience. It is a direct consequence of the causal structure of space-time. The same principle applies to observation. When a telescope captures light from a distant galaxy, it is not seeing that galaxy as it is now, but as it was when the light left it. The image is a record of the past. No amount of technological improvement can eliminate this delay. You can build bigger telescopes, collect more light, and see fainter objects, but you cannot see them in real time if they are far away. This turns astronomy into a kind of archaeology. Every observation is a glimpse into a different era of the universe's history. Now, shift focus to computation and information processing. At first glance, these might seem like areas where relativity does not play a major role. After all, computers operate at speeds much slower than the speed of light. But as devices become smaller and faster, relativistic effects begin to matter. Inside a modern processor, signals move through circuits at a significant fraction of the speed of light in the material. When the size of a chip shrinks to the scale of a few millimeters or less, the time it takes for a signal to cross the chip becomes comparable to the time it takes for the processor to perform a basic operation. This means that the speed of light sets a fundamental limit on how quickly different parts of a computer can communicate with each other. Engineers already have to account for these delays when designing high-speed circuits. They arrange components to minimize signal travel times, synchronize operations carefully, and manage the flow of information to avoid errors. As technology continues to advance, these constraints become more pronounced. You cannot build a processor where all parts update instantly, because instantly is not a meaningful concept when signals take time to propagate. This has led to the development of parallel computing architectures, where many operations are carried out at once, rather than trying to push a single sequence of operations faster and faster. In this sense, relativity nudges technology towards certain design patterns, favouring distributed systems over centralised ones. Another area where relativistic limits appear is in the storage and transmission of energy. Any device that stores energy in a field, such as a capacitor or an inductor, relies on the finite speed at which changes in the field propagate. When you charge a capacitor, the energy flows into the electric field between the plates. That flow is guided by electromagnetic signals that move at the speed of light. This means that even in small, everyday devices, there is a finite time associated with changing energy states. In high-power systems, such as electrical grids or particle accelerators, these effects become more noticeable. Engineers have to account for the propagation of signals and energy through long cables, waveguides, and fields, all of which operate under the same light speed limit. In particle accelerators, for example, the timing of electromagnetic fields that push particles forward has to be synchronized with extreme precision. A tiny mismatch in timing, on the scale of nanoseconds or less, can cause particles to miss the accelerating phase and lose energy. This level of precision is directly tied to the fact that signals propagate at a finite speed. Another technological frontier influenced by relativity is navigation and timing. Global positioning systems rely on satellites equipped with atomic clocks. These clocks tick at rates that are affected by both their speed and their position in Earth's gravitational field. If these relativistic effects were ignored, the system would accumulate errors of several kilometers per day. This means that everyday navigation, from finding a route on a phone to guiding aircraft and ships, depends on corrections derived from the geometry of space-time. This is a striking example of how abstract ideas about time dilation and gravitational effects have practical, tangible consequences. Now think about the challenge of building structures or machines that operate at very high speeds or energies. As you push technology into these regimes, you begin to encounter not just engineering limits, but physical ones. Materials have maximum strengths. But even if you imagine materials that are arbitrarily strong, you still face the problem of energy cost. To accelerate a large object to a significant fraction of the speed of light requires an enormous amount of energy. That energy has to come from somewhere. It has to be generated, stored, and controlled. The sheer scale of the required energy makes certain ideas, like accelerating a macroscopic spacecraft to near-light speeds, extremely challenging. This does not mean it is impossible in principle, but it means that the technological and economic hurdles are enormous. Another consequence of relativistic limits is how they shape the design of sensors and detectors. High-energy particles move close to the speed of light. Detecting them requires instruments that can respond on extremely short timescales. These detectors often rely on light itself, capturing tiny flashes produced when a particle passes through a material. The timing of these flashes can be used to reconstruct the particle's path and energy. The precision of these measurements is limited by how quickly the detector can respond and how accurately it can measure the arrival times of photons. This brings the speed of light into the heart of the measurement process. At even smaller scales, quantum effects become important. The uncertainty principle sets limits on how precisely certain quantities can be known at the same time. When combined with relativistic constraints, this creates a complex landscape of possibilities and limits. For example, there are theoretical limits on how much information can be stored in a given region of space, based on its energy and size. These limits are connected to ideas about black holes and entropy. This suggests that there are fundamental bounds on computation and information storage that are rooted in the structure of space-time itself. Another area where these limits appear is in the transmission of signals through extreme environments. Near massive objects, space-time is curved. Light paths bend. Signals can be delayed or redshifted. Any technology that operates in such environments has to account for these effects. For instance, if you were to place a communication relay near a black hole, the signals it sends and receives would be distorted by the intense gravitational field. The timing and frequency of the signals would change in predictable ways, but those changes would have to be carefully managed. This is not just a theoretical curiosity. Similar, though much smaller effects occur near Earth and have to be accounted for in satellite communication and navigation systems. Another technological challenge shaped by relativistic limits is the idea of synchronization. In everyday life, you can set clocks to the same time and assume they stay in sync. In a relativistic universe, synchronization depends on the frame of reference. Two clocks that are synchronized in one frame may not be synchronized in another. This becomes important in systems that span large distances and move relative to each other, such as satellite networks or distributed sensor arrays. Engineers have to choose a reference frame and define synchronization procedures that work within that frame. This choice is not arbitrary. It affects how data is time-stamped, how events are ordered, and how systems coordinate their actions. Now, consider the idea of building technology that approaches the fundamental limits, such as extremely high-energy accelerators or ultra-precise clocks. As you push closer to these limits, you often find that improving one aspect makes another more difficult. For example, making a clock more precise often requires isolating it from environmental influences, such as vibrations and electromagnetic noise. But isolating it also makes it harder to interact with, to read out its time, or to integrate it into a larger system. Similarly, increasing the energy of a particle accelerator often requires making it larger, because the particles need more distance to be gradually accelerated. This leads to machines that span kilometers, or even tens of kilometers, reflecting the practical consequences of the speed of light limit and the energy-speed relationship. Another subtle influence of relativity on technology is in the way it shapes expectations. Science fiction often imagines faster-than-light travel and instantaneous communication as convenient tools. In a universe where the speed of light is a firm boundary, these ideas remain speculative. This does not mean that creativity is stifled. It means that technological imagination has to work within a different set of constraints. Ideas like generation ships, where multiple generations live and die during a long journey to another star, or robotic explorers that send back information over decades or centuries emerge from this framework. These ideas are shaped by the recognition that distance and time are deeply connected. Another interesting technological frontier is the attempt to test the limits themselves. Physicists design experiments to look for tiny deviations from the predictions of relativity, such as slight variations in the speed of light under different conditions. So far, these experiments have found no evidence of such deviations, reinforcing the idea that the speed of light is a universal constant. But the search continues, because any deviation would point to new physics beyond our current understanding. This interplay between theory and technology is a recurring theme in the history of science. New ideas inspire new instruments, and new instruments test and refine the ideas. Relativity is no exception. The development of precise clocks, high-energy accelerators, and sensitive detectors has allowed physicists to probe the structure of space-time in ways that were once unimaginable. At the same time, the results of these experiments feed back into the design of new technologies, shaping everything from communication systems to navigation tools. Another area where relativistic limits play a role is in the control of large-scale systems. Consider something like a space elevator, a hypothetical structure stretching from Earth into space. The stability of such a structure would depend on the propagation of mechanical and electromagnetic signals along its length. These signals would travel at finite speeds, meaning that different parts of the structure could not respond instantly to changes. This would have to be taken into account in any design, adding another layer of complexity. Similarly, in large, distributed power grids or communication networks, delays in signal propagation can lead to instabilities if not properly managed. These are practical examples of how the finite speed of information transfer shapes the behaviour of complex systems. Another technological domain influenced by relativistic limits is the study of high-speed imaging. Capturing events that happen on extremely short timescales, such as chemical reactions or the motion of electrons in materials, requires techniques that use ultra-fast pulses of light. These pulses can be as short as a few femtoseconds, a tiny fraction of a second. Even at these scales, the speed of light plays a role in determining how the pulses are generated, shaped, and detected. This shows how the same fundamental limit appears at both the largest and smallest scales of technology. Now, step back and look at the broader pattern. In a relativistic universe, technology is always working with delays, with finite propagation speeds, with energy costs that grow as you push closer to fundamental boundaries. These are not just obstacles, they are also guides. They shape the kinds of systems that are stable, efficient and practical. Distributed systems, autonomous devices, layered communication networks, and energy-efficient designs all reflect an adaptation to these constraints. In this sense, the structure of space-time itself becomes a kind of silent engineer, influencing the shape of human invention. Richard Feynman often spoke about the pleasure of finding out how the world works, not just in theory, but in practice. He enjoyed showing how deep principles show up in everyday phenomena and in the tools people build. The limits imposed by relativity are a clear example of this. They connect the motion of galaxies to the design of microchips, the ticking of atomic clocks to the navigation of spacecraft. As these connections become clearer, it becomes easier to see technology not as something separate from the laws of nature, but as something that grows within them, shaped and guided by the same rules that govern stars and particles. After tracing the reach of engines, signals and machines across a universe shaped by quiet boundaries, it can feel natural to let the pace ease, to step away from the language of limits and designs, and simply notice what it means to exist inside a world governed by a small set of steady numbers. These constants do not announce themselves in daily life. They do not shimmer in the air or mark the horizon. Yet they are present in every breath, every step, every flicker of light that reaches your eyes. The speed of light is one of these constants, but it is not alone. There is the strength of the electromagnetic interaction that holds atoms together, the gravitational constant that shapes the motion of planets and stars, the constants that set the masses of particles and the charges they carry. Together, these values define the stage on which all motion, all structure, and all change unfolds. To return to stillness in this context does not mean imagining a universe without movement. It means pausing to consider the deeper layer beneath motion, the layer of rules that remains unchanged while everything else flows. Think for a moment about the idea of a constant itself. In everyday language, a constant is something that stays the same. In physics, it is a number that appears in the equations describing the universe, a value that has been measured and tested across countless experiments and observations, and that seems to hold everywhere and everywhen. These constants are not like the properties of a particular object. They do not belong to a star or a planet or a particle. They belong to the universe as a whole. The speed of light, for example, is not something that light decides to have. It is a property of space-time itself. It tells you how space and time are connected, how fields evolve, how causes and effects are arranged. When you slow down and look at the world through this lens, everyday experiences take on a slightly different character. The warmth of sunlight on your skin is not just heat. It is energy carried by electromagnetic waves that have travelled across millions of kilometres of space, guided by the same constant speed that shapes the geometry of the cosmos. The sound of a voice in a room is a vibration in air, but the forces that hold the air molecules together and allow them to pass the vibration along are electromagnetic in nature, governed by the same constants that shape atoms and stars. Even the feeling of weight, the sense of being pulled toward the ground, is an expression of how mass and energy curve space-time, following rules that involve the gravitational constant and the speed of light. These connections can make the world feel more unified, less like a collection of separate phenomena, and more like different expressions of a single, underlying framework. Another way to approach this stillness is to think about what does not change, even as everything else does. Galaxies form and drift apart. Stars are born and burn out. Planets cool, erode and reshape themselves. Life evolves, adapts, and transforms. Through all of this, the constants remain the same, as far as we can tell. The speed of light measured in a laboratory today matches the speed of light inferred from distant galaxies billions of years ago. The strength of the electromagnetic force appears to be the same across the observable universe. This persistence is not just a curiosity. It is what allows the universe to be intelligible. If these values changed from place to place or moment to moment, the laws of physics would not have a stable form. Predictions would fail. Patterns would break. The fact that these constants hold steady is what makes science possible in the first place. There is a kind of quiet reliability in this. While everything you can see and touch is temporary, the framework that allows you to see and touch it appears to endure. Now, consider how this framework shapes the idea of stillness itself. In a relativistic universe, there is no absolute rest. Motion is always relative. You can be at rest with respect to the ground beneath your feet, but the Earth is rotating and orbiting the Sun. The Sun is moving through the galaxy. The galaxy is drifting within a larger cosmic structure. From another perspective, you are always in motion. Yet there is a sense in which you can be still. You can choose a reference frame, a way of slicing space-time into space and time, and within that frame you can define what it means to be at rest. This choice is not privileged. It is a practical decision, not a statement about the true state of the universe. This flexibility can feel unsettling at first, but it also carries a kind of freedom. There is no single, universal viewpoint that all others must conform to. Each observer has their own, equally valid way of describing the world. What remains the same across all these viewpoints are the constants and the relationships they define. The speed of light is the same for everyone. The basic form of the laws is the same for everyone. The structure of cause and effect is the same for everyone. This shared foundation is what allows different perspectives to be reconciled into a single, coherent picture. Returning to stillness can also mean reflecting on how much of the universe is beyond direct experience. The distances between stars and galaxies are so vast that light itself takes years, centuries, or longer to cross them. Most of what exists in the universe lies outside your current causal horizon. Its light has not yet reached you. Its influence has not yet arrived. This does not mean it is separate in a deep sense. It means that the structure defined by the speed of light and the age of the universe places a boundary around what you can know right now. This boundary is not fixed. As time passes, light from more distant regions reaches you. Your observable universe grows. But there will always be a limit, because the universe is expanding and because light has a finite speed. This creates a kind of moving edge to knowledge, a horizon that advances but never disappears. There is a quiet symmetry in this. Just as you cannot see beyond a certain distance in space, you cannot see beyond a certain distance in time. The future is also beyond reach. You can influence it, but you cannot observe it. The past arrives to you as light and signals. The future remains a set of possibilities. Both are shaped by the same constants and the same causal structure. Another aspect of stillness emerges when you think about the idea of equilibrium. Many physical systems left on their own tend towards states of balance. Temperatures even out, pressures equalize, chemical reactions reach a steady state. These tendencies are guided by deeper principles, like the second law of thermodynamics, which is itself connected to the structure of time and the flow of energy. The constants of nature set the scales for these processes. They determine how strongly particles interact, how easily energy is transferred, how quickly systems can move toward equilibrium. In this sense, the constants are like the background rhythm of the universe. They set the tempo for change. Even in a system that seems still, like a rock resting on the ground, there is constant motion at smaller scales. Atoms vibrate, electrons move, fields fluctuate. This microscopic activity does not usually show up in the macroscopic behaviour of the rock. It averages out, creating the appearance of stillness. This layering of motion and stillness is another way the universe balances change and stability. Now consider how this balance shows up in the human experience of time. On one level, time feels like a steady flow, a river carrying you from past to future. On another level, moments can feel suspended, as if the flow is slowed or paused. From a physical perspective, time is tied to change. If nothing changes, there is no way to measure the passage of time. In a universe governed by constants, change happens within a structured framework. The rules do not change, but the states of systems do. This allows for both predictability and novelty. You can predict how a system will behave under certain conditions, but the specific details of what happens can still surprise you. Richard Feynman often spoke about this balance. He liked to point out that physics is about finding patterns, but also about embracing the fact that nature has an element of unpredictability, especially at the quantum level. The constants provide the pattern. The events provide the variation. Returning to stillness in this sense can mean appreciating the pattern without needing to follow every variation. Another way to think about this is through the idea of scale. The constants of nature connect the very small to the very large. The same speed of light that governs the behaviour of subatomic particles also governs the expansion of the universe. This connection across scales is one of the remarkable features of modern physics. It suggests that the universe is not a collection of separate domains, each with its own unrelated rules, but a single, integrated system. When you look at the night sky, you are seeing light that has travelled across vast distances, carrying information about stars and galaxies. That light is described by the same equations that describe the behaviour of a laser in a laboratory. This unity can make the cosmos feel closer, even as it remains immense. There is also a kind of stillness in the idea of invariance. Many of the laws of physics are invariant under certain transformations. You can shift your position, rotate your orientation, or change your state of motion, and the laws remain the same. This means that the universe does not care where you are or how you're moving. The same rules apply. This impartiality can feel both humbling and comforting. You're not at the centre of the universe in a physical sense, but you are not excluded from its rules either. The same constants that govern distant galaxies govern the atoms in your body. Another quiet theme that emerges here is the idea of finiteness. The speed of light is finite. The age of the universe is finite. The amount of energy in a given region is finite. These finiteness conditions shape what is possible. They define horizons, limits, and capacities. At the same time, the universe can feel boundless, because within these limits there is an enormous range of structures, patterns, and experiences. Returning to stillness can mean holding both of these ideas at once. There are boundaries, but within them there is vastness. Now, consider the role of constants in shaping the conditions for life. If the electromagnetic force was slightly stronger or weaker, atoms might not form stable structures. If gravity were much stronger, stars might burn out quickly or collapse before planets could form. If the speed of light were different, the relationship between mass and energy would change, altering the balance of processes in stars. These considerations suggest that the constants are finely tuned in a way that allows complex structures to exist. This does not necessarily mean that they were chosen or designed. It can also be approached from the idea that only in a universe with such values could observers arise to notice them. Either way, it adds another layer of depth to the idea of stillness. The framework that remains unchanged is also the framework that makes change, complexity, and awareness possible. Another point of reflection is how constants shape the idea of connection. Because information travels at a finite speed, relationships between distant events are always mediated by delays. This means that the universe is not a single instantaneous whole. It is a mosaic of regions, each with its own local present, connected by streams of light and influence from the past. This mosaic structure can make the universe feel more textured, less like a static block, and more like a dynamic network. Stillness, in this context, is not the absence of motion, but a moment of alignment within this network, a point where local processes settle into a temporary balance. Another way to see this is through the idea of resonance. Systems often respond most strongly to certain frequencies or patterns of input. These resonances are determined by the system structure and the constants that define its behaviour. In atoms, electrons absorb and emit light at specific frequencies. In musical instruments, strings vibrate at specific tones. In the universe as a whole, certain patterns of structure and motion emerge more readily than others. These resonances can be thought of as the universe's way of expressing its underlying framework. Returning to stillness can mean listening for these patterns, noticing the regularities that appear beneath the surface of complexity. Now, bring the focus back to the human scale. Daily life is full of motion, tasks, and concerns. It is easy to move through it without thinking about the deeper structure that supports it. Yet, every moment is embedded in this larger framework of space-time, fields, and constants. The simple act of sitting in a room involves gravitational interaction with the Earth, electromagnetic forces holding the floor and your body together, and light bouncing off surfaces to reach your eyes. All of these processes follow the same rules that govern distant galaxies and subatomic particles. This can lend a sense of continuity between the small and the large, the personal and the cosmic. Richard Feynman often emphasized the joy of noticing these connections. He liked to talk about how understanding the underlying principles of nature can add to the appreciation of everyday experiences rather than taking away from them. Seeing a rainbow, for example, can be enriched by knowing how light refracts and reflects inside droplets of water. The knowledge does not replace the beauty. It adds another layer to it. In the same way, recognizing the role of constants and limits in shaping reality can add depth to the experience of being part of that reality. There is also a kind of stillness in accepting limits. The speed of light sets a boundary that cannot be crossed, at least as far as current understanding goes. This can feel restrictive, especially when thinking about travel to distant stars or communication across vast distances. But it can also be seen as part of what gives the universe its character. Boundaries create structure. They define shapes, patterns, and relationships. A game without rules is not a game. A story without constraints has no form. In this sense, the constants of nature are like the rules of the universe's game. They define what kinds of stories can be told. Another aspect of stillness is the idea of perspective. When you look at the universe on human timescales, everything seems to change quickly. When you look at it on cosmic timescales, many things appear slow and steady. Galaxies rotate over hundreds of millions of years. Stars live for billions of years. The expansion of the universe unfolds over even longer spans. Against this backdrop, a human lifetime is a brief moment. Yet, within that moment, there is a rich experience of time, motion, and connection. Returning to stillness can mean placing that moment within the larger context, not to diminish it, but to see how it fits into a much bigger pattern. Now consider the idea of constants as something like the quiet background of a piece of music. The melody may change, the rhythm may vary, different instruments may come and go, but the key and the tempo provide a consistent framework. The universe's constants play a similar role. They set the key and the tempo for all physical processes. This analogy is not perfect, but it can help convey the sense of an underlying order that remains present even as the details shift. Another thought that often arises in this context is the idea of discovery versus invention. Are the constants of nature discovered, meaning they exist independently of us and we simply measure them? Or are they, in some sense, tied to the way we describe the universe? Most physicists lean toward the idea that these values are features of reality itself. They are not chosen by observers, they are found. This makes the act of measuring them feel like uncovering something that was already there, something that would be there even if no one were around to notice it. This can lend a sense of depth to the idea of stillness. The universe, in this view, has its own structure and rules, independent of any particular observer. Yet, observers are part of that structure. They are made of the same fields and particles governed by the same constants. This creates a kind of reflexive situation. The universe contains within itself the means to observe and describe itself. Returning to stillness, in this light, can mean recognizing that you are both a part of the system and a perspective on it. Another layer of this reflection is the idea of simplicity and complexity. The constants themselves are few in number. The equations that use them can often be written in compact forms. From this simplicity arises an immense diversity of phenomena. This is one of the striking features of physical law. A small set of rules can generate a vast range of outcomes. This can feel almost like a form of creativity built into the universe. As this idea settles, the speed of light and the other constants can be seen less as barriers and more as enabling conditions. They are what make the universe rich and structured rather than chaotic and formless. Another way to approach stillness is to think about what remains when you strip away all the particular details. Remove the stars, the planets, the particles, the fields. What is left is the structure of space-time and the constants that define it. This is, of course, a purely conceptual exercise. You cannot actually remove everything and be left with something. But it highlights the idea that there is a deep layer of description that sits beneath all the specific forms. This layer is where the constants live. Now, bring the focus gently back to the present moment. You're here, reading or listening in a particular place and time. Light from your surroundings is reaching your eyes. Signals from distant parts of the universe are passing through you unnoticed. You're embedded in a web of interactions that stretches across scales from the subatomic to the cosmic. The constants of nature are at work in all of these interactions, quietly, steadily, without pause. Returning to stillness does not require stepping outside this web. It can simply mean noticing it. There is a kind of calm that can come from recognizing that, beneath the constant flow of events, there is a stable framework that holds it all together. This framework does not rush. It does not hurry. It does not change from one moment to the next. It provides a backdrop against which motion, change, and experience can unfold. As this sense of stillness settles, it naturally leaves space for curiosity rather than closure. The constants of nature are measured, but their deeper origin remains an open question. Why do they have the values they do? Could they be different in other universes, if such things exist? Are they truly fundamental, or do they emerge from an even deeper layer of law? These questions do not demand immediate answers. They invite continued exploration. And so, instead of ending with a final statement or a neat conclusion, it can feel more fitting to let the attention drift gently forward, back into the ongoing story of a universe that is both dynamic and grounded, both changing and constant. A universe where every journey, every signal and every quiet moment of awareness unfolds within the same steady framework that light traces across space and time, always present, always guiding as the next questions and the next discoveries wait just beyond the current horizon.